The 43-day hostage crisis. NASA finally breaks silence. The images exist. They have existed for over 40 days now, sitting in a server somewhere deep within NASA's infrastructure, pixel perfect and untouched by human eyes outside a select few. 3 times the resolution of Hubble, side view perspective of the anti-tail, 30 kilometers per pixel spatial resolution captured as 3IATLAS passed within 29 million kilometers of Mars. The HiRISE camera aboard the Mars Reconnaissance Orbiter did its job flawlessly, executing an imaging sequence that planetary scientists had been planning since summer, and then the data just stopped. It stopped because on the same week those images were captured, the United States federal government shut down. Not a partial shutdown, not a temporary hiccup, a full bureaucratic paralysis that would stretch across 43 days, and in that time, the most important astronomical images of the decade sat locked behind red tape while the entire world waited. While amateur astronomers turned their telescopes toward Virgo, hoping to catch a glimpse of something they could barely resolve. While Avi Loeb published article after article cataloguing anomalies that those images might explain or deepen. While Congresswoman Anna Paulina Luna wrote formal letters demanding their release. The data sat there, hostage to protocol. Think about that for a moment. The third confirmed interstellar object ever detected by humanity, displaying behaviour that has the scientific community locked in the most public disagreement in modern astronomy, passing through a region of space where we had the perfect vantage point to capture details we will never get again, and the images were held because communications of NASA News had been suspended. The HiRISE website continued releasing new images of Martian terrain on a daily basis throughout the shutdown. Craters and valleys and dust storms all flowing freely to the public. But 3IATLAS was singled out. Any images of the interstellar comet 3IATLAS are considered NASA-wide news. That was the official statement. As if the bureaucratic designation of newsworthiness should supersede the time-sensitive nature of scientific discovery. Because here is what was happening while those images gathered digital dust. 3IATLAS was moving. It passed perihelion, survived the solar encounter that some predicted would tear it apart, and began its journey back out toward interstellar space. Ground-based observatories were planning follow-up observations, trying to coordinate spectroscopic measurements and photometry that would be infinitely more valuable if they knew what the HiRISE images revealed about the object's structure and jet geometry. Every day of delay meant observations were being planned in partial darkness, researchers making educated guesses about where to point their instruments and what wavelengths to prioritise, all while the data that could guide. Those decisions sat locked away. Loeb was not quiet about this. He called it terrestrial stupidity, a phrase that cut through the usual diplomatic language of academic science. He wrote that scientific knowledge should not be second in priority to bureaucracy. That data, this time sensitive, belongs to humanity, not to the internal procedures of a government agency. He submitted official letters. He spoke to 8 different podcasters and reporters in a single day, explaining over and over why the delay was not just frustrating but actively harmful to the scientific process. And then Luna amplified it, taking the issue directly to acting NASA Administrator Sean Duffy with a formal congressional request. As the government shutdown is about to end, can NASA please release the data that was held hostage by politics for 40 days? The phrase held hostage became the rallying cry, because that is exactly what it felt like to everyone watching this unfold. Not a reasonable delay for calibration or analysis, not a thoughtful pause to ensure data quality. A hostage situation where the hostage takers were not malicious actors, but the grinding machinery of bureaucratic procedure that could not distinguish between routine Mars geology and a once-in-a-lifetime interstellar visitor. And the public noticed. The interest in 3IATLAS had already been building since its discovery, but the shutdown drama pushed it into an entirely different category of attention. Loeb mentioned that his dishwasher repair technician recognised his voice on the phone and immediately started asking about 3IATLAS, a dishwasher repair technician. That is the level of public penetration this story achieved. People who would normally never follow astronomical news were suddenly invested in whether NASA would release these images, what they might show, whether the delay itself was suspicious, which of course fed into the more conspiratorial interpretations. If 3IATLAS were just a normal comet, why the special treatment? Why single it out from all other Mars Reconnaissance Orbiter observations? The official explanation, that it was considered NASA-wide news and therefore subject to different protocols during a shutdown, satisfied almost no one. It felt like circular reasoning. It is special because we designated it special, and because we designated it special, it must be treated specially, and that special treatment means you cannot see it during a shutdown. The logic ate its own tail. But there was another layer to this that made it even more maddening for researchers. China released images. The Tianwen-1 Mars orbiter captured 3IATLAS from roughly the same distance, and the China National Space Administration published those images with minimal delay. Lower resolution than HiRISE, certainly. The Tianwen-1 high-resolution imaging camera has a smaller aperture, 38.7 centimeters compared to HiRISE's 50 centimeter mirror, but they were images. They showed the nucleus surrounded by a coma several thousand kilometers in diameter. They gave the scientific community something to work with while NASA's superior data remained inaccessible. The contrast could not have been more stark. One space agency, operating under a completely different governmental structure, decided that scientific data about an interstellar object should be shared quickly with the global research community. Another space agency, with a long proud tradition of open data policies, with missions like Hubble and James Webb that routinely make their observations publicly available, suddenly found itself unable to release time-critical information because of bureaucratic classifications that no one outside the agency fully understood. Loeb pointed out the bitter irony. NASA missions have set the gold standard for data accessibility. The Hubble archive is legendary for enabling discoveries by researchers who never proposed for telescope time, just by making all observations public after a proprietary period. JWST follows similar policies. Mars missions have generated vast public data sets that anyone can access and analyse. But 3IATLAS, this object that every astronomer in the world wanted to study, that amateurs were staying up until 4 in the morning to photograph with backyard telescopes, that had Kim Kardashian tweeting questions at NASA's acting administrator, this object had its data locked down. The scientific cost was real. Loeb emphasised this repeatedly, trying to cut through the noise of speculation and conspiracy to focus on the practical damage. Astronomers were planning spectroscopic observations for when 3IATLAS emerged from behind the sun in the morning sky. Those observations would be far more valuable if they knew the geometry of the jets, the orientation of the anti-tail, the precise morphology of the coma. Without the HiRISE images, they were essentially flying blind, making their best guesses based on lower resolution data and hoping those guesses were correct. Every week of delay narrowed the window for follow-up observations as 3IATLAS continued to fade and recede. And beyond the immediate scientific implications, there was a deeper issue about trust and transparency. Loeb's argument was not just that NASA should release the images because they were scientifically valuable, though they absolutely were. His argument was that this kind of data gatekeeping, especially around an object generating this much public interest, this many questions, this level of scientific debate, actively undermines public trust in scientific institutions. When people see that the data exists but is being withheld, even for procedural reasons that might be perfectly legitimate, it creates space for doubt. It creates space for theories that the real reason for the delay is something other than bureaucracy, something more sinister. Which brings us to the question that was being asked in every comment section, every Reddit thread, every social media discussion about 3IATLAS during those 43 days. What are they hiding? The rational answer was nothing. They are hiding nothing. There is simply a bureaucratic logjam created by the intersection of a government shutdown and data classification protocols that were never designed with this kind of time-sensitive situation in mind. But that rational answer satisfied fewer people as each day passed. Because if they were hiding nothing, why not just release the images? If it was truly just about protocol, why not make an exception for something this unique, this important, this visible to the public eye? Loeb had an answer for that too, and it was characteristically blunt. He suggested that the delay was not evidence of extraterrestrial intelligence, but rather evidence of terrestrial stupidity. The idea that aliens were somehow involved in the decision to withhold these images was, in his view, giving far too much credit to what was actually just bureaucratic inertia. But that phrase, terrestrial stupidity, landed hard because it captured the frustration that so many people felt. This was not some grand conspiracy. It was something potentially worse. It was institutional dysfunction preventing science from happening at a moment when science needed to happen. The shutdown ended. Luna tweeted that NASA had confirmed they would release the images and data once the government reopened. Multiple sources indicated the release would happen within days. The astronomical community held its breath, because those images, when they finally emerged, would either support the natural comet interpretation, or they would deepen the mystery. They would show whether the anti-tail really was anomalous, or perfectly explicable. They would reveal whether the jets maintained their orientation despite rotation, whether the nuclear showed signs of fragmentation, whether the morphology matched anything we'd seen before in cometary science. But even before those images were released, the 43-day delay had already changed the conversation around 3IATLAS. It had elevated the object from a fascinating astronomical curiosity to something approaching a cultural phenomenon. It had demonstrated that in the age of instant information, when amateur astronomers can capture interstellar objects from their backyards and share the images within hours, the old models of data control and careful vetting before public release feel increasingly anachronistic. It had shown that public interest in space science, when properly engaged, remains enormous, and it had raised uncomfortable questions about how scientific institutions balance legitimate needs for data validation against the public's right to access information about objects that belong to no one nation, that come from beyond our solar system, that represent our only glimpses into the nature of interstellar space. 3IATLAS was discovered in early summer. By mid-autumn it had become more than an astronomical object. It had become a case study in how science communication works and fails in the modern era, how bureaucracy can inadvertently undermine the very missions it is meant to support, and how the simple act of withholding information, even for entirely mundane reasons, can fuel speculation far more exotic than anything the data itself might have revealed. The images were coming. Within days, everyone said. Within days, we would finally see what HiRISE saw when 3IATLAS passed Mars at closest approach. We would see the side view of the anti-tail, the threefold improvement in spatial resolution over Hubble, the details that might settle some arguments or ignite new ones. We would see whether 43 days of waiting, 43 days of frustration and speculation, and increasingly heated public debate had been worth it. Whether the bureaucratic hostage crisis had been protecting anything real, or had simply been protecting procedure for procedure's sake. But in those final days before release, as the world waited for NASA to make good on its promise, there was another development, another anomaly, something that would make the HiRISE images even more critical, even more eagerly anticipated. Because while everyone was focused on the shutdown drama, on the politics and protocols and public pressure, 3IATLAS itself was continuing to reveal itself in ways that defied easy explanation. The 12th anomaly had emerged, and it was possibly the most troubling one yet. The 12th anomaly, jets that refused to spin back in summer, astronomers measured the rotation period of 3IATLAS, 16.16 hours, give or take 1/100th of an hour. A remarkably precise measurement for an object so distant, derived from the periodic variations in its brightness as different surfaces turn toward Earth. 16 hours and roughly 10 minutes for one complete rotation, not unusual for a cometary nucleus. Many comets spin at similar rates, tumbling through space as they journey through the solar system. The rotation itself was unremarkable. What happened next was not. The new images started appearing in early autumn. Wide-field photographs from experienced astrophotographers capturing 3IATLAS as it emerged from behind the sun into the morning sky. And what those images showed made no sense in the context of that 16-hour rotation. Jets extending outward from the nucleus, reaching distances of 1 million kilometers toward the sun, 3 million kilometers in the opposite direction. Tightly collimated streams of material, maintaining their orientation across vast distances. Jets that should have been smeared into spirals by rotation but were not. Think about what rotation does to outflowing material. If you are standing on the surface of a spinning object and you release gas or dust, that material carries the rotational velocity with it as it moves away. Like water spraying from a rotating lawn sprinkler, the stream curves. It has to curve. The mathematics are inescapable. As the source rotates, the angle of emission changes continuously, and material ejected at different times ends up at different angles, creating a spiral pattern that winds tighter or looser depending on the rotation rate and outflow speed. For 3IATLAS, with its 16-hour rotation period, you can calculate exactly what that smearing should look like. The jets would need to traverse 1 million kilometers, which at the expected thermal speed of sublimated volatiles from a natural comet, roughly 400 meters per second, takes about a month. During that month, 3IATLAS would complete approximately 45 full rotations, 45 complete spins while material is travelling from the nucleus outward. The jets should look like peas in a pod, discrete puffs of gas separated by the distance material travels during one rotation period, 23,270 kilometers between each puff. 43 distinct blobs spread across a 1 million kilometer jet. The images showed nothing like this. The jets were smooth, continuous, maintaining fixed orientations despite the rotation that should have turned them into spiraling segmented structures. It was as if the rotation simply did not affect the outflow direction, which made no physical sense for any natural mechanism anyone could propose. Loeb published the analysis immediately. The 12th anomaly, he called it, adding to a list that had been growing since summer. And this one was particularly troubling because unlike some of the other anomalies, which could potentially be explained by unusual but natural properties, this one challenged basic physics. You cannot escape the geometry of rotation. You cannot have sustained outflow from a spinning source without that spin affecting the outflow pattern. Unless the source is not actually spinning, or unless the outflow is not actually sustained over the time periods required, or unless something else is happening that we do not understand. The first possibility, that 3IATLAS stopped rotating, seemed implausible. Asymmetric outgassing from a comet typically enhances rotation, rather than slowing it down. Like a Catherine wheel firework, jets firing preferentially from one side create torque that spins the nucleus faster. There are theoretical scenarios where outgassing could slow rotation, but they require very specific geometries and are generally not efficient. For 3IATLAS to have spun down from its measured summer rotation rate to something negligibly slow would require sustained, perfectly balanced jets acting as brakes, and we have no evidence of such jets before perihelion. The second possibility was more interesting. Perhaps the jets were not continuous. Perhaps they were pulsed, turning on and off with the rotation period in such a way that they only emitted material when oriented in specific directions. This could happen if the ice pockets responsible for outgassing were located in deep valleys surrounded by mountains that shadowed them, except when the sun hit at just the right angle. When illuminated, they would sublimate vigorously. When shadowed, they would cool rapidly and stop outgassing. This on-off behaviour could theoretically create jets that maintained orientation despite rotation. But there were problems with this explanation too. For it to work, you would need the jets to pulse at exactly the rotation period, emitting only when pointed in the right direction. This would create those peas in a pod structures, discrete puffs separated by the rotation period distance. And those puffs should all point generally toward the sun, because ice only sublimates when heated by sunlight. The moment it falls into shadow, molecular speeds drop and outgassing stops, so all the material should be emitted sunward. Yet the images clearly showed jets pointing away from the sun as well. Strong, prominent jets extending millions of kilometers in the anti-solar direction, which could not be explained by sunlight, driven, pulsed outgassing from shadowed valleys. The third possibility was fragmentation. Maybe what looked like tightly collimated jets were actually the trails of fragments that had been ejected from the main nucleus near perihelion. If the nucleus had exploded, throwing off pieces in various directions, and those pieces were now travelling outward on ballistic trajectories, they might create linear features that would not be smeared by the parent body rotation, because they were no longer attached to the parent body. They were flying free, each fragment leaving its own trail of sublimating material. This was testable. If the jets were fragment trails, then high-resolution imaging should reveal multiple discrete nuclei, each at the head of its own jet. The images that had been released so far did not have sufficient resolution to distinguish individual fragments from a single body, but better images were expected. The Nordic Optical Telescope had captured 3IATLAS and processed the data carefully, filtering out background stars and enhancing faint features. What they showed was a single bright source, one nucleus, not a scattered field of fragments, not a disrupted, dispersing cloud of debris, a coherent object with jets emanating from it. So if the rotation had not stopped, and if pulsed outgassing from shadowed ice could not explain anti-solar jets, and if fragmentation was not occurring, what remained? Loeb offered a fourth possibility, one that most of his colleagues were deeply reluctant to entertain, but that the data was making increasingly difficult to dismiss. What if the jets maintained their directionality, because they were produced by technological thrusters that preserve global orientation for navigation purposes? A spacecraft does not smear its exhaust plumes with rotation, because spacecraft that need to maintain thrust vectors use attitude control. They keep their thrusters pointed in specific directions, regardless of any spin the main body might have. If you wanted to accelerate an object through space efficiently, you would need your engines to fire in consistent directions, not spiral around due to rotation. You would need reaction control systems, gyroscopes or momentum wheels, active stabilization that counteracts rotational forces. This is basic spacecraft engineering. The pushback to this suggestion was immediate and fierce. Jason Wright at Penn State published detailed rebuttals, arguing that every anomaly Loeb had catalogued could be explained by known cometary behaviour, that nothing about 3IATLAS required invoking technology. Other astronomers pointed out that the anti-tail was not unique, that several comets had shown similar sunward features caused by large dust grains that radiation pressure could not push efficiently, that the rotation paradox might simply reflect incomplete data or measurement errors, that extraordinary claims required extraordinary evidence, and so far all we had were ambiguous observations that could be interpreted multiple ways. But Loeb's counter-argument was equally forceful. He pointed out that critics were essentially arguing from analogy. They would take one anomaly and find a single comet somewhere in the historical record that displayed something vaguely similar, then declare that anomaly explained. But 3IATLAS was not displaying one anomaly. It was displaying 12. The probability of a natural object exhibiting all 12 simultaneously was not the probability of each individual anomaly, which might be a few percent, but the product of all those probabilities, which drove the likelihood down to levels that strained credulity. The trajectory aligned with the ecliptic to within 5 degrees, probability 0.2%. the arrival time fine-tuned to bring it near multiple planets, while being unobservable from Earth at perihelion, probability 0.005%. The extreme nickel to iron ratio found in industrially produced alloys, probability below 1%. The extreme negative polarization unprecedented in known comets, probability below 1%. The blue colour near perihelion instead of the expected reddening, unusual but possible. The massive jets requiring implausibly large surface areas to sublimate sufficient ice, physically problematic. The non-gravitational acceleration requiring over 13% mass loss with no corresponding debris cloud, contradictory. And now this. Jets maintaining orientation despite rotation over month-long timescales. Multiply those probabilities together and you get numbers like 1 in 100 million. Loeb calculated it explicitly. The chance of 3IATLAS being a natural object, given all the observed anomalies taken together, was roughly 1 in 100 million. Those were his numbers. Other scientists disputed the calculation, argued that the probabilities were not truly independent, that treating them as multiplicative was statistically naive. But even if you were generous with the uncertainties, even if you assumed the most favourable conditions for natural explanations, you were still left with an object that was behaving very strangely. The rotation paradox crystallised something that had been building through months of observations. 3IATLAS was not acting like the comets we know. It was not acting like 1I Oumuamua, the first interstellar object, which showed no cometary activity at all. It was not acting like 2I Borisov, the second interstellar object, which looked and behaved almost exactly like a solar system comet. 3IATLAS occupied a strange middle ground, active like a comet, but active in ways that seemed inconsistent with cometary physics, displaying jets and outgassing and non-gravitational acceleration, but displaying them in configurations that violated expectations, and the most frustrating part, the aspect that made this scientific debate feel more like trench warfare than collaborative inquiry, was that the observations needed to resolve these questions were difficult and time-consuming to obtain. Spectroscopy could measure the velocity of the jet material, determine if it was moving at the few hundred meters per second expected from thermal sublimation, or the few kilometers per second that might indicate artificial propulsion. But 3IATLAS was faint and getting fainter, requiring long integration times on large telescopes, and those telescopes had competitive proposal processes with many scientists requesting time. Getting the observations scheduled and executed took weeks or months. High-resolution imaging could potentially resolve the nucleus directly, measure its size and shape precisely, look for surface features or structures that might indicate composition or origin. But 3IATLAS was small and distant, and even Hubble could only resolve it as a fuzzy blob with a tail. The HiRISE images from Mars might have better resolution, but they were still locked away, and even when released they would show 3IATLAS as it appeared near perihelion, not as it appeared now. Direct sampling was obviously impossible. We have no missions en route to intercept 3IATLAS. No spacecraft could reach it in time. By the time we could launch something, even with advanced propulsion, 3IATLAS would be far beyond the outer solar system, unreachable. Whatever we were going to learn about this object, we would learn it from telescope observations during its brief passage through the inner system. And that passage was already half over. The closest approach to Earth would come in mid-December. After that, 3IATLAS would fade rapidly as it receded, becoming too faint for detailed study within months. So the scientific community was in a race against time and geometry. Every clear night was precious. Every spectrum, every photometric measurement, every high-resolution image was irreplaceable data that might either support the natural interpretation or deepen the mystery. And hanging over all of it was the awareness that we might never see another object like this. Interstellar visitors are rare. 1I Oumuamua appeared once in centuries of astronomical observation. 2I Borisov came just 2 years later, but that might have been luck. There was no guarantee we would detect another interstellar object in our lifetimes. 3IATLAS might be our only chance to study an interstellar visitor that showed activity, that gave us something to analyse beyond just its trajectory. The jets that refused to spin were just the latest puzzle piece, the 12th anomaly in a growing collection. And as the astronomical community absorbed this new information, as the arguments intensified between those who insisted on natural explanations and those who suggested we should at least consider alternatives, another story was developing, one that would take the 3IATLAS phenomenon beyond the realm of academic astronomy into something approaching popular culture. Because while scientists debated rotation periods and jet collimation, Avi Loeb was about to do something that would make headlines around the world. He was about to place a bet, a very public, very specific, very bold bet about the future of humanity's search for extraterrestrial intelligence. And 3IATLAS was at the centre of it, 1 in 100 million Loeb places. The bet of the century. Michael Shermer is the executive director of the Skeptics Society. For decades, he has been one of the most prominent voices arguing against extraordinary claims, from paranormal phenomena to conspiracy theories to, yes, alien visitation. He is the person you call when you want someone to explain why the exciting claim is probably wrong, why the anomaly is probably mundane, why we should default to natural explanations until the evidence becomes truly overwhelming. So when Avi Loeb approached Shermer with a proposal for a formal wager, the symbolism could not have been more perfect. The bet was simple and specific. By December 31st, 2030, 5 years from now, there will be undisputable scientific evidence for a technological artifact from an extraterrestrial civilization. Not ambiguous signals, not statistical anomalies that could be interpreted multiple ways. Undisputable evidence, the kind that would satisfy even skeptics, even the scientific mainstream, even NASA administrators who currently issue statements assuring the public that 3IATLAS is just a comet. That kind of evidence. The Long Now Foundation agreed to officiate the wager. This is an organisation dedicated to long-term thinking, to projects and questions that span decades or centuries rather than quarterly reports or election cycles. They maintain a registry of long bets, public wagers about future events that help clarify thinking about what is possible, what is probable, what we should expect from the trajectory of human knowledge and technological development. Loeb and Shermer's bet would join that registry. The stakes were not personal profit. Any winnings would go to the non-profit Galileo project, the organisation Loeb founded specifically to search for technological signatures of extraterrestrial origin. Loeb's statement to the Long Now Foundation laid out his reasoning. The search for technological artefacts has just started in earnest, with the discovery of the anomalous interstellar object 3IATLAS, the launch of the Rubin Observatory, and the construction of 3 Galileo Project observatories. We are entering a new era of capability. For the first time in human history, we have instruments sensitive enough and systematic enough to actually detect interstellar visitors, to study them in detail, to potentially identify technological signatures if they exist. The combination of new telescopes, new missions, new analytical techniques, and new willingness to take the question seriously means that the next 5 years will sample the possibilities in ways previous decades could not. The bet announcement landed like a bomb in the scientific community. Some saw it as confidence, even bravery. Loeb was putting his reputation on the line in the most public way possible. If undisputable evidence emerged by 2030, he would be vindicated. If it did not, he would have lost a very visible wager to one of the world's most prominent skeptics. Other scientists saw it as showmanship, a publicity stunt designed to keep Loeb's name in headlines and maintain public interest in his work. Still others saw it as deeply irresponsible, raising expectations for discoveries that were unlikely to materialise and setting up the public for disappointment when the 5-year deadline passed without alien artefacts being confirmed. But the bet did something important, regardless of motivation or likely outcome. It forced clarity. It replaced vague speculation about whether we are alone in the universe with a concrete falsifiable prediction about what we will discover in a specific time frame. It moved the conversation from philosophy to empiricism. Either we will find undisputable evidence by 2030 or we will not. There is no ambiguity in the bet's terms, no wiggle room for reinterpretation. It succeeds or fails cleanly. And Loeb was explicit about what would constitute winning. Not a radio signal that could be natural pulsars misidentified, not a chemical signature in an exoplanet atmosphere that might indicate biology, but might also indicate geology, not another ambiguous interstellar object like 1A, where natural and artificial explanations remain in heated debate. Undisputable evidence, which meant either direct detection of a technological object or signals so clearly artificial that no natural process could explain them, or physical samples recovered and analysed showing unambiguous signs of manufacturing. The bar was high, deliberately high. 3IATLAS sat at the centre of this bet, whether explicitly named or not. The timing was not coincidental. Loeb placed the wager just as 3IATLAS was emerging from behind the sun, just as new observations were beginning to flow in, just as the HiRISE images were supposedly days away from release. He was making a statement. This object, with its 12 anomalies and 1 in 100 million probability of natural origin, might be the artifact the bet depends on, or it might not. But even if 3IATLAS turns out to be natural, Loeb was arguing, the mere fact that we are now detecting and studying interstellar objects means we will find others, and sooner or later, one of them will be technological. The mathematics of the bet were worth examining. 5 years. In that time, how many more interstellar objects might we detect? The Rubin Observatory, which just achieved first light, will survey the sky with unprecedented depth and cadence. It will detect faint, fast-moving objects that previous surveys missed. Estimates suggest it might find 1 to 10 interstellar objects per year once fully operational. So over 5 years, conservatively, 5 to 50 interstellar visitors. If even one of those shows clear technological signatures, Loeb wins the bet. But there was another pathway to victory that did not require more interstellar objects. The Galileo Project observatories were designed to detect unidentified aerial phenomena, objects in Earth's atmosphere or near space, that exhibit characteristics inconsistent with known human technology or natural phenomena. 3 observatory sites were under construction, equipped with sensors spanning the electromagnetic spectrum, capable of tracking fast-moving objects and collecting data that could distinguish between conventional aircraft, weather phenomena, and potential unknowns. If any of these observatories captured clear evidence of a technological object of non-human origin, that would satisfy the bet's terms. Shermer's position was equally clear. Though he had not yet made a formal public statement about his side of the wager at the time Loeb announced it, but Shermer's entire career provided the context. Extraordinary claims require extraordinary evidence. The human tendency toward pattern recognition, toward seeing agency and intention in random events, toward believing we are special and therefore likely to encounter other special things, creates a strong bias toward false positives. We want to find aliens. We want to believe we're not alone. That desire shapes perception. It makes ambiguous data seem more significant than it is. It turns statistical anomalies into discoveries prematurely. The history of SETI and UFO research is littered with signals and sightings that seemed compelling initially but dissolved under scrutiny. So Shermer would argue, and any skeptic would agree, that betting against undisputable evidence in 5 years was the safe, rational choice, not because alien civilizations do not exist necessarily, but because detecting them is hard. Space is vast. Technological civilizations might be rare. Even if they are common, finding their artifacts in the enormous volume of the galaxy is like finding specific grains of sand on all the beaches of Earth. The fact that we have not found any yet, despite decades of searching, suggests they are either very rare or very distant or very good at remaining undetected. None of these factors are likely to change dramatically in 5 years. Yet Loeb's optimism was not baseless. He pointed to the exponential growth in observational capability. The telescopes coming online in the next few years are not incrementally better than what came before. They are orders of magnitude more sensitive, faster, more comprehensive in their coverage. Rubin will image the entire visible sky every few nights. The square-kilometre array will listen to the radio universe with unprecedented sensitivity. The extremely large telescope will resolve exoplanet atmospheres with spectroscopic precision that could detect industrial pollutants. These are not small improvements. They are qualitative leaps in what we can observe. And there was a deeper argument embedded in Loeb's position, one that made the bet about more than just probability and detection capability. It was about scientific culture, about how the astronomical community responds to anomalies, about whether we are willing to seriously investigate the hypothesis that some of what we observe might be technological rather than natural. Loeb argued that decades of dismissing any such suggestion as unscientific, as career suicide, as the domain of cranks and conspiracy theorists had created a blind spot. We were not looking because we assumed we would not find anything. But if you do not look, you cannot find. The bet was partly a challenge to that assumption. Consider the history. 1A accelerated as it left the solar system. Non-gravitational acceleration, just like 3IATLAS. The natural explanation offered was outgassing, but 1A showed no visible coma, no tail, no evidence of the volatile sublimation that supposedly caused the acceleration. When Loeb suggested that solar radiation pressure on a thin light sail could explain the acceleration without requiring invisible outgassing, the response was not "let us investigate this carefully." The response was dismissal, ridicule in some quarters. The argument that proposing alien technology was a violation of Occam's razor, even though invoking invisible outgassing from a cometless comet was hardly simpler. The bet was Loeb saying enough of dismissing possibilities without investigation, enough of using parsimony as a shield against uncomfortable hypotheses, enough of treating the search for technological signatures as inherently less legitimate than the search for biosignatures or habitable exoplanets. If we are serious about the question of whether we are alone, then we need to be serious about looking for all types of evidence, including evidence of technology. And if we look seriously, with proper instruments and open minds, Loeb was betting we will find something within 5 years. The reaction on social media was predictably divided. Loeb's supporters praised his willingness to make a concrete prediction. His critics called it a publicity stunt. The general public, many of whom were following the 3IATLAS story with intense interest, saw the bet as validation. Here was a prominent scientist confident enough in his analysis to stake his reputation on a timeline. That meant something. It meant this was not just idle speculation or attention-seeking. It meant Loeb genuinely believed the evidence was pointing toward discovery. But there was risk in the bet beyond personal reputation. If 5 years passed and no undisputable evidence emerged, it would strengthen the skeptical position enormously. It would be used as ammunition by those who argue that the search for technological signatures is a waste of resources, that we should focus on more probable avenues of research. It would make it harder for future scientists to get funding for SETI projects or techno-signature surveys. The bet, in other words, had consequences beyond just Loeb and Schirmer. It had consequences for an entire field of inquiry. Yet perhaps that was the point. Perhaps the function of the bet was not really to predict the future, but to change it. By creating a deadline, by attaching stakes and public visibility to the question, Loeb might be accelerating the very research that could win the bet. Scientists who might not have proposed for telescope time to study interstellar objects might now do so, aware that the next few years are crucial. Funding agencies might prioritize projects related to techno-signature detection, knowing that the field is in the spotlight. The bet creates momentum. It turns the search for technological artifacts from a marginal pursuit into something with urgency and importance. And there was one more element to consider. the psychological effect on observers. For decades, the search for extraterrestrial intelligence has been characterized by patience. We acknowledge it might take centuries to find anything. We frame it as a multi-generational project with no guarantee of success in our lifetimes. This creates a certain passivity. We search, but without real expectation of results soon. The bet disrupts that. It says, no, this could happen in 5 years, in your lifetime, maybe even this decade. That changes how people engage with the question. It makes it urgent rather than abstract. 3IATLAS was the catalyst. Without its anomalies, without the intense public interest it generated, without the scientific debate about its nature, Loeb probably does not place this bet at this time. The object provided the perfect context. An actual interstellar visitor, in our solar system right now, displaying behaviour that a Harvard astrophysicist argues is inconsistent with natural origins. You cannot get better setup for a bet about finding technological artefacts. Whether 3IATLAS itself turns out to be the evidence that wins the wager, or just the opening act that led to later discoveries, it had already served a purpose. It had made the question real. It had moved the discussion from theoretical possibilities to concrete observations requiring explanation. 5 years. By the end of 2030, we would know. Either undisputable evidence would have emerged, vindicating Loeb and forcing a massive re-evaluation of humanity's place in the cosmos. Or it would not, strengthening the position that while alien civilizations may exist somewhere, detecting their artifacts remains beyond our current reach. The bet was placed, the clock was running, and 3IATLAS, still speeding through the solar system with its unexplained jets and impossible rotation properties, continued to defy easy answers. But the object itself was not finished revealing its secrets. While everyone focused on the bet, on the political drama of withheld images, on the scientific arguments about jet collimation, 3IATLAS was about to demonstrate something even more surprising. Something that would make skeptics uncomfortable and believers more confident. The object that was supposed to have broken apart near the Sun had not broken apart at all. The object that survived what should have killed it. The predictions were specific. Given the massive non-gravitational acceleration detected near perihelion, given the jets extending millions of kilometres, given the calculated mass flux of 5 billion tonnes per month, 3IATLAS should have lost substantial mass during its solar encounter. More than 13% according to those momentum conservation calculations. For a typical comet, that kind of mass loss creates drama. Massive coma development, dust clouds, debris, and frequently fragmentation. The nucleus breaks apart under thermal stress, tidal forces, or the violence of sustained outgassing. Comets fragment all the time. It is one of the most common outcomes for comets that pass close to the Sun, especially large comets experiencing rapid heating. So when 3IATLAS emerged from behind the Sun in autumn, astronomers pointed their telescopes expecting to see pieces, multiple nuclei, perhaps a cluster of fragments trailing each other in orbit, or possibly no nucleus at all, just a dispersing cloud of debris marking where a comet used to be. The betting among planetary scientists was not whether 3IATLAS had fragmented, but how many pieces it had broken into. The object that went behind the Sun should not be the same object that came out the other side, not after what it experienced at perihelion. The Nordic Optical Telescope was among the first to get clear images. David Jewett and Jane Liu, both veterans of small body observation, analysed the data carefully. They applied multiple processing techniques, linear stretching to enhance faint features, contouring to reveal structure, colour mapping to highlight differences, spatial filtering that subtracted background signal in concentric rings around the brightest pixel, a technique that reveals faint jets and asymmetries that might be invisible in raw images. They examined the result from every angle, and what they saw was unequivocal. A single body, one nucleus, not fragments, not a debris field, not a dissolving cloud. 3IATLAS had survived perihelion intact, This was breaking news, literally announced with that phrase at the top of Loeb's analysis. The interstellar object 3IATLAS did not break up near the Sun. Images taken on the date showing a single body with no evidence for breakup following the perihelion passage 2 weeks earlier. The image showed the anti-tail clearly visible, pointing toward the Sun as it had been doing since summer. The resolution was approximately 500,000 kilometers wide, meaning that any fragment separated by more than tens of thousands of kilometers would have been distinguishable. There were none. 3IATLAS remained coherent. This was surprising. More than surprising. It was problematic for the natural comet interpretation. The calculations that predicted substantial mass loss were straightforward. The non-gravitational acceleration measured by NASA required ejecting material with significant momentum. For gas ejected at thermal velocities, typical of sublimating ice warmed by sunlight, the mass required to produce that acceleration was large. More than 13% of the total mass. You do not lose 13% of your mass quietly. You do not maintain structural integrity while evaporating more than 1/10 of yourself in the space of a month. Look at the energetics. To sublimate 5 billion tons of carbon dioxide, the primary volatile detected in 3IATLAS's coma, requires enormous energy. Carbon dioxide ice needs 600 joules per gram to sublimate. Multiply that by 5 billion tons, and you get 3 times 10 to the 18th joules. Where does that energy come from? The Sun. At perihelion distance, roughly 200 million kilometers, the Sun delivers 700 joules per square meter per second. To collect 3 times 10 to the 18th joules over a month requires an absorbing area of 1,600 square kilometers. That is the area of a sphere with a diameter of 23 kilometers. But the Hubble Space Telescope imaging gave an upper limit on the nucleus diameter of 5.6 kilometers, 4 times smaller than required. The absorbing area would be 16 times smaller than needed. Even if the entire surface were perfectly absorbing, perfectly efficient at converting sunlight to sublimation energy, it would not be enough, not even close. For water ice, the most common cometary volatile, the situation was even worse. Water requires more energy per gram to sublimate, pushing the required diameter to 51 kilometers, nearly 10 times larger than observed. So either the measurements were wrong, or the calculations were wrong, or something about the scenario did not match our assumptions. The measurements seemed solid. The Hubble imaging was clear. The non-gravitational acceleration was detected at statistical significance. The jet images showed material extending to the distances claimed. The problem was in the assumptions, specifically the assumption that sunlight-warming ice was responsible for the jets. If the jets were not thermally driven, the energetics changed completely. Chemical rockets expel exhaust at 3 to 5 kilometers per second, 10 times faster than thermal sublimation. That reduces the mass required by a factor of 10, making 13% mass loss drop to 1.3%, suddenly much more consistent with an object maintaining integrity. Ion thrusters reach even higher exhaust velocities, 10 to 50 kilometers per second. At those speeds, the required mass fraction drops to well below 1%. A spacecraft using advanced propulsion could produce the observed acceleration while losing only a small fraction of its mass, easily consistent with remaining intact. But this explanation required accepting that 3IATLAS was technological, that its jets were thrusters, that the non-gravitational acceleration was not outgassing but propulsion. This was the line most scientists refused to cross, not because the physics did not work, but because the implications were so profound. Accepting that 3IATLAS survived perihelion intact without fragmenting meant accepting that either our understanding of cometary physics was deeply wrong, or the object was not a comet. Loeb pressed the argument hard. He pointed out that natural comets displaying jets of the scale seen around 3IATLAS do not maintain cohesion. They fragment. We have observed this repeatedly. Comets that undergo massive outgassing episodes fall apart. The stress is too great. The nucleus is too weak. just a loose agglomeration of ice and rock held together by its own feeble gravity. When you start ejecting substantial fractions of the mass, when you develop jets powerful enough to push material millions of kilometers against the solar wind, the structural forces exceed the gravitational binding and the nucleus disintegrates. Yet 3IATLAS was still there. Single object, coherent. Yes, the image showed jets. Yes, there was clearly substantial activity. The antitail extended toward the sun, visible proof that material was being expelled. But the nucleus itself, the central condensation, remained singular. This combination, intense activity plus structural integrity, was difficult to reconcile with natural cometary behaviour. The counter-arguments came swiftly. Some planetary scientists argued that the mass loss estimates were wrong, that Loeb had made errors in his calculations or unrealistic assumptions about ejection velocities. Perhaps the jets were not as massive as they appeared. Perhaps the gas density was lower than calculated. Perhaps the outflow speeds were higher than the thermal values assumed, which would reduce the required mass. There were papers disputing each step of the analysis, each intermediate calculation, trying to find room for a natural comet to survive without fragmentation, while still producing the observed jets. Others pointed out that we have incomplete information. The images showing a single body had limited resolution. Maybe there were fragments, just too close together to distinguish in the available observations. Maybe the nucleus had cracked but not fully separated, remaining as a contact binary or a loose cluster barely held together by gravity. Maybe future observations with better resolution would reveal the fragmentation that must have occurred given the energetics. But as more images came in, this explanation weakened. The Virtual Telescope project captured 3IATLAS repeatedly. Gianluca Massi, who ran the project, processed images from different dates, tracking the object as it climbed higher in the morning sky. Each image showed the same thing, a compact central source with extended jets, no obvious fragmentation, no cluster of nuclei. The object looked like a single, coherent body surrounded by its coma and tails. If it had broken up, the pieces were extraordinarily close together, close enough that even telescopes with arc-second resolution could not separate them. And there was another detail that made fragmentation unlikely. The jets maintained their structure. If the nucleus had shattered into many pieces, each piece trailing its own plume of sublimating material, you would expect to see a confused, chaotic coma. Multiple jets at random angles, each fragment contributing its own outgassing direction. Instead, the images showed organized structure, a prominent anti-tail toward the sun, a longer tail in the anti-solar direction, additional jets at specific angles. This organization suggested a single source, not a rubble pile of fragments, each doing its own thing. Loeb published a calculation. Given the jet velocities and the solar wind pressure, the mass density at a distance of 1 million kilometers from 3IATLAS must be several million proton masses per cubic centimeter. This is dense. Dense enough that the solar wind pressure pushing against it stops the antitail at roughly 1 million kilometers. You do not get that kind of density from a fragmented, dispersing nucleus. You get it from a coherent source producing sustained, directed outflow. The debate reached a level of intensity unusual even for astronomy, a field not normally known for public arguments. Both sides dug in. The natural comet proponents insisted that we just needed more data, better observations, refined calculations, that every anomaly would eventually find a natural explanation, because invoking technology was premature, unscientific, a violation of the principle that extraordinary claims require extraordinary evidence. The technology proponents, led by Loeb but joined by a small but growing number of researchers willing to publicly entertain the hypothesis, argued that refusing to consider technology despite mounting evidence was itself unscientific, that letting theoretical prejudice override observational data was exactly what good science should not do, and the public watched. The story of 3IATLAS surviving its solar encounter became another data point in the growing narrative that this was not a normal comet. News outlets reported it. Social media discussed it. The bet with Shermer gained new relevance. If 3IATLAS really was defying natural explanations, if it really was intact when it should have shattered, maybe Loeb would win his wager. Maybe within 5 years we would have undisputable proof. Maybe the proof was already here and we were just arguing about interpretation. The timing was also significant. Just as the world was waiting for NASA to release the HiRISE images, just as everyone was debating bureaucratic delays and data access and what those images might show, 3IATLAS itself was providing new data by simply existing, by being observable, by continuing its journey through the solar system as a single object rather than a fragmented debris field. The images from Nordic Optical Telescope, from the Virtual Telescope project, from amateur astronomers waking up at 4 a.m. to photograph it, were all confirming the same basic fact. This object was still here, still intact, still defying predictions. But if those ground-based images were surprising, what might the HiRISE images show? Those images taken from Mars orbit with their 30 km per pixel resolution, their side-view perspective of the anti-tail, their coverage of 3IATLAS during its closest approach to that planet, might reveal details invisible from Earth. They might show surface features, subtle asymmetries, jet source locations. They might provide the evidence needed to definitively answer whether 3IATLAS was natural or technological. Or they might, as seemed increasingly likely, simply provide more data for both sides to interpret according to their preferred theories. The survival of perihelion was not just about structural integrity, it was about what that integrity implied. A natural comet, subjected to the stresses 3IATLAS experienced, should not stay together. The fact that it did meant either the stresses were less than calculated, which required questioning the observations, or the object was stronger than a typical comet, nucleus, which required explaining why. And the why was where the interpretations diverged. Natural explanations invoked unusual composition, maybe more rock than ice, maybe some binding strength from prior evolutionary history in interstellar space. Technological explanations invoked engineered materials, structural elements designed to withstand acceleration and thermal cycling. Neither explanation could be ruled out by the data available, and that was perhaps the most frustrating aspect of the entire 3IATLAS saga. Every new observation, every new analysis, every new image provided more information but not more clarity. The object remained stubbornly ambiguous, acting like a comet in some ways, unlike any known comet in other ways, displaying activity that demanded explanation while defying the explanations typically offered. It was as if 3IATLAS had been designed specifically to maximize scientific uncertainty and debate. Whether that design was by nature or by intelligence was the question that could not yet be answered definitively. But even as scientists argued about perihelion survival and structural integrity, the public was about to get something it had been waiting for all autumn. Not the HiRISE images, which remained frustratingly delayed despite promises of imminent release. Something else. Something more immediate and accessible. The world was about to watch 3IATLAS in real time. Live. Through telescopes streaming directly to the internet. The Virtual Telescope project had scheduled an event, and for one night, millions of people would be able to see for themselves this object that had consumed so much attention, generated so much debate, and refused to give simple answers. The live stream was coming, and whatever 3IATLAS revealed during those hours of observation would become part of the permanent record, witnessed by anyone with an internet connection and a curiosity about what travels between the stars. Tonight's live stream the world watches. 3IATLAS. Escape. The announcement came with specific timing. 11:15 post-meridium Eastern Standard Time. The Virtual Telescope project, operating from Manciano, Italy, would turn its suite of robotic telescopes toward the constellation Virgo and broadcast what they captured live to the world, weather permitting. That caveat always hangs over ground-based astronomy, the reality that billions of dollars of equipment and carefully orchestrated observing plans can be defeated by clouds. The live stream had already been delayed once. The original scheduling had it earlier, but poor weather forced a postponement. Now conditions looked favourable. Clear skies forecast, stable atmosphere, good transparency. The stars were aligning, quite literally. This was not the first time the Virtual Telescope project had hosted public events. Gianluca Massi had built a reputation for making astronomy accessible, for showing people what professional-grade instruments could see, for demystifying the process of observation. Comets, asteroids, planets, even satellites passing overhead, all had been subjects of previous live streams. But 3IATLAS was different. The interest level was orders of magnitude higher. This was not just astronomy enthusiasts tuning in. This was mainstream news outlets embedding the stream. This was social media influencers promoting it. This was people who had never watched a telescope live stream in their lives clearing their schedules because they wanted to see the object everyone was talking about. The anticipation built through the day. Forums discussed what the live stream might reveal. Would the anti-tail be visible? Would the jets show structure? Would 3IATLAS appear as a bright compact source, or would the coma be extended and diffuse? These were questions that still images could answer, but there was something different about watching live. The immediacy, the sense that you were seeing it now in this moment, as it actually looked right now, rather than in archived data from days or weeks prior. Even though light from 3IATLAS took minutes to reach Earth, even though in that sense all observation is looking at the past, the psychological experience of live observation felt more connected, more real. The equipment list was published. A Moravian C3-61000 EC monochrome CMOS camera, the Artec 250 f4.5 astrograph, software bisque paramount mount. These names meant little to non-astronomers, but signified serious capability. The Artec telescope had a 250mm aperture, enough light-gathering power to see faint objects. The CMOS camera was sensitive and low noise. The mount was rock steady, able to track objects precisely as Earth rotated. This was not amateur gear. This was the kind of setup that produces publishable science. The Virtual Telescope project operated multiple instruments remotely. That was the beauty of modern observational astronomy. The telescope sat in Manciano, a small town in Tuscany with dark skies and good seeing conditions. The operators could be anywhere. Massi controlled the observations from his location, commanding the telescopes via internet, receiving data in real time, processing it, and streaming it out to viewers around the world. The physical location of the astronomer and the physical location of the telescope did not need to match. You could observe the cosmos from your living room, your office, your mobile phone while riding the bus. The photons travelled 93 million miles from the Sun to 3IATLAS, reflected off, travelled another several hundred million miles to Earth, passed through the atmosphere, focused through the telescope optics, converted to electrons in the sensor, digitized, transmitted across fibre optic cables and wireless networks, rendered on screens everywhere. A chain of physical processes connecting human eyes to an interstellar visitor, via technology. As the scheduled time approached, viewing numbers climbed. The YouTube embed showed thousands watching, then tens of thousands. The count kept rising, people from different time zones adjusting their schedules, Europeans staying up late, Americans tuning in during their evening, Asians watching in the morning, global astronomy, everyone looking at the same object at the same time. The chat scrolled rapidly, comments in multiple languages speculating about what they would see, asking questions about the observation process, expressing excitement or skepticism depending on their perspective on the 3IATLAS debate. The stream began with context. Massi explained the current position of 3IATLAS in Virgo, low in the morning sky from the Italian observation site. He discussed the challenges, The object was still relatively close to the horizon, meaning observations had to look through more atmosphere, creating turbulence and absorption. The moon was present in the sky, adding light pollution that made faint features harder to detect. These were not ideal conditions, but they were the conditions available. You observe when you can observe, not when you wish you could observe. The first images appeared. Dark field with scattered stars. The exposure time was noted, 30 seconds. In that 30-second integration, the camera collected photons from 3IATLAS, building up signal against the background noise. When the image displayed, there it was. Not a dramatic bright comet with a sweeping tail like popular imagination might envision. A small, diffuse glow, fuzzy. The central condensation visible, but the edges of the coma blending into background. It looked almost unimpressive at first glance. Just another faint smudge among the stars. But then the processing began. Massey applied contrast adjustments. Suddenly the structure became clearer. The coma was not symmetrical. There was elongation, direction, the beginnings of a tail. He stacked multiple exposures, combining several 30-second images to reduce noise and enhance faint signals. More detail emerged. The tail extended farther than visible in single frames. The ion tail, ionized gas pushed by the solar wind, showed as a narrow spike extending away from the sun direction. And there, visible even in these conditions, the hint of a symmetry pointing sunward. The anti-tail. The chat exploded. People were seeing what they came to see. Confirmation that 3IATLAS was active, that the jets were real, that the features described in scientific papers and argued over in academic journals were actually there to observe. This was not a point of light. This was an extended object with structure, with tails, with that strange anti-tail pointing the wrong direction. Every new processed image brought more comments, more reactions, more people tagging friends to watch. Massey continued the explanation. He discussed how ion tails form, the interaction between the solar, wind and cometary gas creating charged particles that align with magnetic fields and stream away from the sun. He noted that dust tails were different, pushed by radiation pressure, often broader and more curved than ion tails. He pointed out that 3IATLAS was displaying both types of tail, evidence of both gas and dust in its coma. This was cometary behavior. This was what comets do as they warm and vent volatiles. From this observation alone, you would conclude natural comet. But then he addressed the anomalies. The anti-tail was not supposed to be there, or rather it could be there if composed of very large dust grains that radiation pressure could not push effectively, grains that could exist on the sunward side before eventually getting swept away. But the scale was unusual, the brightness was unexpected, and combined with all the other strange properties 3IATLAS had shown, that anti-tail sitting there visible in the live stream images took on greater significance. It was not just an interesting feature, it was evidence in an ongoing debate. The stream continued for an hour, multiple images captured and processed, different exposure times tested. Longer exposures brought out fainter details but risked saturating the bright core. Shorter exposures preserved the nuclear region but lost the faint tail structure. Massey balanced between these extremes, giving viewers both close-ups of the central coma and wide-field shots showing the full extent of the tails. The ion tail stretched visibly, a narrow stream of glowing gas extending across the field of view. The dust tail was broader, more diffuse, and that anti-tail, controversial and unexplained, remained visible throughout the observation. Questions came in the chat. Can you estimate the size of the nucleus? No, Massey explained. The coma is too bright. The nucleus is buried inside that glowing cloud of gas and dust. We see the coma, not the solid surface beneath. The nucleus could be kilometers across or tens of kilometers. We cannot tell from this data. What we see is the atmosphere 3IATLAS has created around itself, the envelope of sublimated material that makes it visible from Earth. The actual rocky icy core is unresolved. hidden at the centre. How fast is it moving? Fast by human standards, Massey noted, over 130,000 miles per hour. But from Earth, watching from hundreds of millions of miles away, that motion is imperceptible in real time. You cannot see it move during the observation. Only by comparing images taken hours or days apart can you measure its motion across the background stars. Tonight, in this hour of watching, 3IATLAS appears stationary, frozen in place among the constellations, but it is racing, every second more than 30 miles closer to interstellar space, every minute nearly 2,000 miles farther from the Sun, every hour over 100,000 miles along its hyperbolic trajectory. By the time the stream ended, 3IATLAS had travelled more than the distance from Earth to Moon, but no one watching could see that motion. Space is too large, distances too vast for human perception to grasp the speeds involved. Are there spacecraft observing it? Yes and no. Some spacecraft caught glimpses as it passed near their orbits, but no mission was designed to intercept 3IATLAS, no probes en route. We are observing purely from afar, using telescopes on Earth and in Earth orbit, watching this visitor pass through without any direct contact. It will come no closer than it already has. From here on out it recedes. Every future observation will be of a more distant, fainter object. What we see tonight is better than what we will see next week. What we saw last week was better than tonight. The observational window is closing, not rapidly, but inevitably. In months, 3IATLAS will be too faint for anything but the largest telescopes. In years, it will be beyond even their reach. This object, which occupied so much attention this autumn, will fade from view and continue its journey unwatched by human eyes. That impermanence added poignancy to the live stream. People were witnessing something finite, a moment in cosmic time when an interstellar object happened to pass through our neighbourhood, and we happened to have the technology to see it, and the awareness to look. In the billions of years before humans existed, countless interstellar objects must have passed through unobserved. In the potentially billions of years of future cosmic time, more will pass. We exist in this tiny sliver where we can see and understand what we are seeing. The livestream participants were among the few billion humans alive at the exact moment when 3IATLAS was visible, and among the much smaller number who chose to watch. They were witnesses to something that would not repeat. The stream drew toward its conclusion. Massey thanked viewers. He noted that more observations were planned, that the virtual telescope project would continue tracking 3IATLAS as long as conditions permitted. He encouraged people to submit their own observations if they had access to telescopes. Every data point mattered. Every image added to the collective understanding. Amateur contributions had been significant in cometary astronomy historically, and 3IATLAS was no exception. Already amateurs had captured images showing jet details that professional observations missed, simply because they happened to observe at the right time with the right equipment. The democratization of astronomy meant that important discoveries could come from anywhere. As people logged off, reactions flooded social media. The live stream had delivered. Not dramatic revelations that would settle the natural versus technological debate, but confirmation, visual evidence that 3IATLAS was real, active, displaying the features that made it scientifically interesting. For skeptics, it was proof that this was just a comet doing comet things. For believers in the technological hypothesis, it was proof that something weird was happening, that the anti-tail was genuinely there, and not just an artifact of image processing. Both camps could watch the same livestream and come away with their views reinforced. The ambiguity persisted even in live observation. But for the general public, the people who are not planetary scientists or astrobiologists, but just curious humans wondering about 3IATLAS, the stream provided something valuable. Connection. They'd seen it themselves now. Not filtered through scientific papers or news reports, but directly through telescope feeds showing the actual object in real time. That directness mattered. It made 3IATLAS more real, more concrete, less abstract. Before, it was just a name, a topic, a controversy. After watching the live stream, it was an actual thing they had witnessed with their own eyes. A fuzzy, glowing object in Virgo with tails extending into the darkness of space. An interstellar visitor making its once and only appearance in human observable history before vanishing back into the cosmic ocean. The viewing numbers peaked at over 100,000 simultaneous watchers. That was extraordinary for a telescope live stream. It suggested the level of public interest had reached something unusual. People cared. They wanted to know. They were willing to spend an hour watching grainy black and white images of a faint comet, because that comet represented something larger. A question about where we stand in the universe. Whether we're alone, whether intelligence exists beyond Earth, whether some of what we see in the sky might be the work of minds, rather than the product of mindless physical processes. 3IATLAS became more than itself through that process. It became a symbol, and symbols have power beyond their physical reality. The object itself was just a collection of ice and rock and possibly metal, travelling on a trajectory determined by gravity and initial conditions from its formation billions of years ago. But the meaning humans attached to it, the debates it sparked, the attention it commanded, the way it made millions of people look up and wonder, that was emergent. That was not in the physics, that was in the interpretation. And as the live stream ended and people returned to their lives, 3IATLAS continued on, indifferent to human attention, indifferent to scientific controversy, following the path it had followed for longer than humans have existed. But humans were not indifferent to it. The conversation would continue, the arguments would persist, and soon, very soon, another chapter in the 3IATLAS story would begin, one that would make even skeptics pause, one that no one had quite predicted. Because while scientists argued and the public watched live streams, something else was happening, something that would demonstrate just how far the reach of 3IATLAS had extended into popular consciousness. The object had been tweeted about by a Harvard physicist. It had been debated by planetary scientists. It had been photographed by amateur astronomers worldwide. But what happened next would show that the cultural penetration went deeper still, all the way to celebrity, all the way to unexpected places, all the way to people who shaped public discourse in ways that transcended science. The internet was about to break, as they say, and 3IATLAS was the reason. From Harvard to Kim Kardashian, how a comet broke the internet. The tweet was direct. 4 words followed by 6 question marks. Wait, what's the T on 3IATLAS? The account had 130 million followers. Kim Kardashian, reality television personality, business mogul, one of the most followed people on social media, was asking NASA about an interstellar comet. The collision of celebrity culture with astrophysics happened in that moment, and the internet did what the internet does when worlds collide. It exploded. The response came from NASA's acting administrator Sean Duffy. Professional, measured, reassuring. Great question. NASA's observations show that this is the 3rd interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. 2 sentences crafted to calm public concern while confirming the object's interstellar origin. No aliens. That phrase would echo through countless follow-up discussions, quoted and requoted, meaned and remixed, treated with everything from relief to suspicion depending on who was interpreting it. But the fact that such a response was needed, that a NASA administrator felt compelled to personally reply to a celebrity tweet about 3IATLAS, spoke volumes about where the story had gone. This was no longer confined to scientific journals and astronomy forums. This had reached the level of pop culture. When Kim Kardashian asks about your research subject, you have achieved a kind of fame that transcends academic citations. You have entered the realm where grandmothers at Thanksgiving dinner know the name, where late-night talk show hosts make jokes, where people who cannot name a single currently active spacecraft know about the weird comet that might be aliens. How did it get here? How did 3IATLAS travel from an observation in Chile to Harvard astrophysicist papers to congressional letters to one of the most famous people on the planet asking questions? The pathway was not straightforward. It wound through multiple internet ecosystems, each amplifying and distorting the signal in characteristic ways, until the story had evolved from scientific curiosity to cultural phenomenon. It started with Loeb's blog posts. He published on Medium, a platform that anyone could access, writing detailed technical analyses alongside more accessible pieces explaining the anomalies. The Medium algorithm promoted content that generated engagement. 3IATLAS content generated enormous engagement. Every new post about the object would rack up thousands of views within hours. Comment sections filled with arguments between proponents of natural and technological interpretations. The pieces got shared to Twitter, to Facebook, to Reddit, each share expanding the audience. Reddit was particularly important in the amplification process. Multiple subreddits picked up the story. The astronomy subreddit had technical discussions. The space subreddit mixed news and speculation. The UFO subreddit treated it as potential confirmation of theories they had held for years. The conspiracy subreddit spun it into narratives about government cover-ups and hidden knowledge. Each community interpreted 3IATLAS through its own lens, its own pre-existing beliefs and interests, and each community had members who belonged to other communities, creating cross-pollination. Someone from the astronomy subreddit would mention 3IATLAS in a gaming forum. Someone from the UFO subreddit would talk about it with co-workers. The story spread through social networks like ripples from a stone dropped in a pond. YouTube creators saw opportunity. Videos about 3IATLAS started appearing. Some were careful, presenting the scientific evidence and the competing interpretations fairly. Others were sensationalist, using clickbait titles and thumbnail images of alien spacecraft photoshopped near comets. The algorithm did not distinguish quality from sensationalism. It distinguished engagement. Videos that got clicks, watch time, comments, shares. Those were the videos the algorithm promoted. And sensationalist content often outperformed careful content in those metrics. So the more extreme interpretations gained visibility, even if they represented minority positions in the scientific community. News outlets noticed the social media buzz. 3IATLAS started appearing in science news sections of major publications. Then it jumped to general news. When a congresswoman writes to NASA demanding data release, that is a political story, not just a science story. When an acting NASA administrator has to respond publicly to conspiracy theories, that is newsworthy. When internet forums are flooded with debates about whether an interstellar object is an alien probe, editors decide that is something readers want to know about. The story escalated from niche interest to mainstream coverage. Television followed. Science communicators were invited on news shows to discuss 3IATLAS. Loeb himself appeared on multiple programs, carefully explaining the anomalies while acknowledging that natural explanations remained possible. His opponents, scientists who insisted 3IATLAS was just a comet, also got airtime. The format of television news, with its need for conflict and debate, naturally framed the issue as a controversy. Two sides, arguing, viewers deciding who to believe. This was not how scientific consensus typically formed, through gradual accumulation of evidence and peer review, but it was how public perception formed, through narrative and rhetoric and the performance of confidence. And then there were the memes. Internet culture processed 3IATLAS through humour and irony. Images of the comet with googly eyes added. Jokes about aliens being terrible at stealth if this was their reconnaissance probe. Comparisons to one Oumuamua with captions suggesting aliens were getting bolder. The humour served multiple functions. It made the topic approachable for people who found scientific papers intimidating. It provided emotional release for the tension between wanting to believe in alien visitors and feeling foolish for that wanting. It created community through shared jokes, a sense of being in on something together. By the time Kim Kardashian tweeted, 3IATLAS had been everywhere, but her tweet represented a new threshold. Because Kardashian's audience was not space enthusiasts or science nerds or even general news consumers. Her audience was pop culture, fashion, entertainment, lifestyle. These were people who might never have heard of 3IATLAS through any other channel, and now they were hearing about it because someone they followed for completely unrelated reasons had asked a question. That was the power of celebrity, the ability to introduce topics to audiences that would never have sought those topics out themselves. The question of how much Kardashian actually knew about 3IATLAS was immediately debated. Was this genuine curiosity? Had she been following the story? Or was it social media management, some assistant monitoring trending topics and crafting engagement? The authenticity did not particularly matter to the outcome. The tweet existed. It had been seen by millions. It had received an official NASA response. 3IATLAS was now unquestionably mainstream. Other celebrities chimed in. Not A-list names like Kardashian, but verified accounts with significant followings. Musicians, actors, comedians, athletes, all suddenly tweeting about an interstellar comet. Some jokes, some genuine questions, some conspiracy theories. The diversity of responses reflected the diversity of interpretations the object inspired. 3IATLAS had become a Rorschach test. What you saw when you looked at it depended on what you brought to the looking. Elon Musk, whose opinions on space topics carried weight given his role running SpaceX, weighed in. He noted that while 3IATLAS was not threatening now, its potential to cause continental scale damage could not be ignored. This was technically true of any large fast-moving object, but coming from Musk it sounded more ominous. His tweet got dissected for hidden meanings. Was he suggesting we should be worried? Was he building narrative for future SpaceX missions? Was he just commenting casually without deeper agenda? The ambiguity allowed people to read their own concerns into his words. The scientific community watched this circus with mixed feelings. On one hand, public interest in space science was fantastic. More people than ever were paying attention to astronomical research. Kids were asking parents about interstellar objects. Schools were incorporating 3IATLAS into lesson plans. The engagement was real, and it was positive for the field generally. On the other hand, the signal-to-noise ratio was abysmal. For every accurate article about 3IATLAS, there were 10 sensationalized videos claiming certainty about alien origin. For every careful analysis, there were 100 forum posts mixing facts and speculation indiscriminately. The public was interested, but were they actually learning anything accurate? Loeb himself was conflicted. He had always advocated for making science accessible, for engaging the public, for breaking down the ivory tower mentality that kept research isolated from ordinary people. 3IATLAS achieving pop culture status was in some sense exactly what he wanted, except the conversation had gotten away from the science. The actual observations, the mathematical analyses, the careful reasoning that led to considering technological hypotheses, all of that was getting buried under layers of interpretation and distortion. When Kim Kardashian asks about the tea, she's not asking for a peer-reviewed paper, she's asking for drama, and drama does not require accuracy. Yet there was something democratic about the process. Science had traditionally been gate-kept. You needed credentials, access to journals, understanding of technical language, connections to people in the field. 3IATLAS was being discussed everywhere by everyone. Amateur astronomers were contributing observations. Internet forums were debating the probability calculations. YouTube creators were explaining orbital mechanics to audiences of millions. The quality was variable, but the access was universal. Anyone with internet connection could participate in the conversation about what 3IATLAS was and what it meant. That had never been true for previous astronomical discoveries. This was new, and the attention was having real effects. The pressure on NASA to release the HiRISE images came partly from congressional oversight, but mostly from public demand. Hundreds of thousands of people were waiting for those images, talking about them, speculating about why they were delayed. That kind of sustained attention made bureaucratic inertia harder to maintain. Someone at NASA had to be thinking about the optics of withholding data that this many people wanted to see. The normal calculus of data release, which balanced calibration needs against proprietary periods against publication priorities, did not account for viral interest. The rulebook had not been written for scenarios where interstellar objects became social media phenomena. The cultural moment also provided opportunity for education. Neil deGrasse Tyson, perhaps the most famous science communicator in the world, talked about 3IATLAS on his podcast. He explained what made it scientifically interesting while tempering expectations about alien technology. He discussed the difference between possibility and probability, a distinction that often got lost in internet discourse. Other educators used 3IATLAS as a teaching moment for orbital mechanics, spectroscopy, the scientific method, the nature of evidence. The object was a hook that let them reach audiences who might otherwise tune out during science discussions. But education competed with entertainment, and entertainment often won the engagement metrics. Videos titled 3IATLAS Proves Aliens Exist got more views than videos titled Calculating the Mass Loss Rate of an Interstellar Comet. Accuracy was valuable, but it was not optimized for algorithms. The algorithms promoted what kept people watching, clicking, sharing, and controversy kept people engaged more reliably than careful explanation. So the most viewed content about 3IATLAS often strayed furthest from scientific consensus. This was not unique to this story. This was how internet information ecosystems function generally. But it felt particularly problematic here because the underlying science was genuinely interesting and did not need sensationalizing to be compelling. The breakthrough to mainstream via Kardashian marked a peak. After that tweet, interest began to plateau, not decline, but level off. The story had reached saturation. Everyone who was going to hear about 3IATLAS had heard. The next developments would keep the existing audience engaged but would not dramatically expand it. This was the natural life cycle of internet phenomena. The exponential growth phase could not sustain indefinitely. Eventually you run out of new people to tell. But the plateau was still at an extraordinary level compared to typical astronomy stories. Months after discovery, 3IATLAS remained in public consciousness. People who did not follow space news knew the name. When new observations were released, they made headlines. When Loeb published new analyses, they got covered in major outlets. The object had staying power. It was not a one-day sensation that vanished from feeds by the next news cycle. It persisted. And that persistence mattered because the story was not over. There were still observations to come, debates to resolve, questions to answer. The celebrity moment had expanded the audience for whatever came next. What came next, as it happened, was something that would please the visual learners and confuse everyone else. New images began circulating showing 3IATLAS with increasingly complex tail structures, not just the simple ion tail and dust tail of a normal comet. Multiple jets, multiple plumes, asymmetries and protrusions that defied easy categorization. The tail was growing, and as it grew, it revealed structure that astronomers had not quite expected. Structure that would add yet another layer to the ongoing mystery of what exactly 3IATLAS was and why it behaved the way it did. The growing tail was about to become the next chapter in a story that refused to simplify itself, no matter how much the public or the scientists wanted simple answers. The growing tail, mystery, multiple jets, defy. Natural explanation. The images from astronomers Jaeger, Riemann and Prosperi showed something extraordinary. Not one tail, not two. 4 to 5 distinct jets fanning out from the nucleus in multiple directions. A complex structure that looked more like a fountain than a simple comet tail. Each jet visible as a separate stream of material, each with its own orientation and extent. The overall pattern resembled the tail structure of comet C 2016 R2, an unusual long-period comet known for being extremely rich in carbon monoxide and nitrogen but poor in dust. That comparison was interesting because C 2016 R2 was itself considered anomalous. Normal comets do not look like that, so comparing 3IATLAS to an already unusual comet was not exactly reassuring to those hoping for conventional explanations. The tail was growing. Each new set of observations showed it extending farther from the nucleus, not just lengthening in the expected anti-solar direction, but developing structure, complexity, multiple components that behaved somewhat independently. The main ion tail, pushed by solar wind, reached millions of kilometers, but there were also the jets pointing toward the sun, the anti-tail that should not exist or should be much smaller than observed. And now these additional features, streams at angles that did not align neatly with either solar radiation pressure or solar wind direction. Gianluca Massi captured the evolution over several days. Images from early in the month showed a relatively simple structure: the nucleus with a diffuse coma, one prominent tail. But as 3IATLAS climbed higher in the morning sky, as observing conditions improved, as more integration time allowed fainter features to become visible, the complexity became apparent. The object was surrounded by a network of streams and jets that did not follow the simple patterns expected from solar forces acting on sublimating ice and dust. The morphology raised immediate questions about composition and activity level. For multiple distinct jets to persist simultaneously, you need multiple active regions on the nucleus surface, each venting material in its own direction as the nucleus rotates. This is possible. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, showed multiple active regions producing separate jets. But 67P was studied up close. We could see its surface, identify the specific locations where jets originated, understand why they pointed where they pointed based on local topography and illumination angles. 3IATLAS was being observed from hundreds of millions of kilometers away. We could see the jets, but not their source regions. The nucleus itself remained unresolved, hidden inside its coma. The growing tail was particularly interesting in the context of 3IATLAS, having passed perihelion weeks earlier. Typically, comets are most active near perihelion when solar heating is strongest. As they move away from the sun, activity decreases. The coma shrinks. The tails fade. You see peak brightness around perihelion, then decline as the comet recedes. 3IATLAS was showing the opposite pattern. It was getting more active as it moved away from the sun. The tail was growing. The jet structures were becoming more prominent. This was backwards. Loeb suggested several possibilities. One was delayed activity. Maybe ice beneath the surface had been warmed during perihelion, but took time to conduct that heat inward, and now deeper ice was sublimating as the stored thermal energy propagated through the nucleus. This could create an activity peak after perihelion rather than during. It was not common, but it had been observed in some comets. The mechanism required specific thermal properties in the nucleus material, conductivity and heat capacity values that allowed for slow thermal diffusion, but it was physically plausible. Another possibility was that the apparent increase in activity was actually an observing geometry effect. Near perihelion, 3IATLAS was behind the sun from Earth's perspective, difficult to observe. Now it was emerging into better viewing geometry, higher in the sky before dawn, farther from solar glare. Maybe the tails had been this extensive near perihelion, but we simply could not see them well. Now that we could see the object clearly, we were observing the full extent of its activity that had been present all along but obscured. This was the more conservative explanation, and it probably accounted for some of what was being observed. But there was a third possibility that Loeb raised more cautiously. What if the jets were not purely thermal? What if some component of the outflow was driven by mechanisms other than sunlight warming ice? chemical reactions could potentially store and release energy on timescales independent of solar distance. Subsurface phase changes, crystallization of amorphous ice, other exothermic processes might contribute to activity that peaked at unexpected times. Or, returning to the technological hypothesis, active propulsion could be increasing rather than decreasing, as 3IATLAS adjusted its trajectory for whatever destination or purpose it had. The composition question came back into focus. Spectroscopic observations had shown that 3IATLAS was rich in carbon dioxide, unusually rich. The 4% water content by mass was far below the typical value for solar system comets, which are mostly water ice with other volatiles as minority constituents. Carbon dioxide sublimates at lower temperatures than water. It becomes active farther from the sun. A comet with high carbon dioxide content might continue showing strong activity well beyond perihelion as that carbon dioxide sublimated from deeper layers. This could explain sustained or even increasing tail development post-perihelion. But the extreme nickel to iron ratio complicated the composition story. That was not explained by carbon dioxide-rich ice. That required either highly unusual chemistry in the formation environment, or, alternatively, industrially produced materials. Every attempt to build a coherent natural explanation for all of 3IATLAS's properties ran into similar problems. You could explain one anomaly by invoking specific conditions. You could explain two anomalies with somewhat contrived but possible scenarios. Explaining all 12 simultaneously required stretching the probability space so thin that skepticism became reasonable. The multiple jets also related back to the rotation paradox. If 3IATLAS was rotating every 16 hours, and if these jets were persistent features visible over many days, they should show rotational smearing. The jets should spiral. They should look like the pattern a rotating lawn sprinkler creates. But they did not. They appeared as distinct straight or gently curving streams. Either the rotation had stopped, which required explaining how that happened, or the jets were not continuous during rotation, only activating when specific surface regions faced the sun, or something about the jet production mechanism did not couple to rotation the way thermal outgassing should. Astrophotographer Satoru Murata captured a particularly striking image showing the intricate structure in the tails, multiple components clearly visible, the spike like anti-tail prominent on one side, broader diffuse tails extending in other directions, and there in the same field of view, galaxy NGC 4691, a reminder that this cosmic drama was playing out against a background of unimaginably distant structures. The galaxy, millions of light years away, photons travelling for millions of years to reach the camera, 3IATLAS, travelling for billions of years through interstellar space before entering the solar system. Both captured in the same frame, connected by nothing but the accident of observing geometry that placed them visually near each other in our sky. The image was beautiful and scientifically valuable simultaneously. It showed the tail complexity while providing positional reference that could be used to measure 3IATLAS's motion across the celestial sphere. Amateur contributions like Murata's were becoming essential to understanding 3IATLAS. Professional observatories had scheduled time on large telescopes, but they observed sporadically. Nights when conditions were good, when the object was at the right elevation, when other targets did not take priority. Amateurs observed continuously. Every clear night, multiple photographers around the world were pointing instruments at Virgo, capturing whatever 3IATLAS looked like at that moment. This created a time series that professional observations alone could not match. And that time series revealed variability. The tail structure changed. Not just growing longer, but changing shape. Jets that were prominent one night might be fainter the next. New features appeared. The anti-tail brightness varied. This variability was important information. It suggested that whatever was producing the jets was not steady state. The activity pulsed, fluctuated, responded to something. Solar wind variations could cause changes in ion tail brightness, as the density and speed of the wind changed. Rotation of the nucleus would cause brightness changes as different surfaces turned toward Earth. Genuine variations in outgassing rates, driven by whatever processes controlled activity, would create temporal changes in tail structure. Disentangling these different causes required careful observation and analysis. Some astrophotographers reported seeing the tail glow green in their images. Green emission from comets typically comes from diatomic carbon molecules, C2, excited by solar ultraviolet radiation. The molecules absorb high-energy photons, electrons jump to excited states, then fall back down emitting characteristic green light. Many comets show green comet. 3IATLAS displaying green emission was not anomalous. It confirmed that carbon compounds were present in the coma, being ionized and excited by sunlight. But the intensity of the green emission, compared to emissions at other wavelengths, could provide information about composition and activity level. More detailed spectroscopy would be needed to quantify this, but even the visual green glow visible in amateur images was a data point. The tail was also hiding structure. Commenters on the published images noted that in some processing, you could see the tail was not uniform. There were striations, concentric shells, features suggesting that material was being ejected in pulses rather than as a steady stream. This pulsed ejection could be rotational. As the nucleus spins, active regions turn on and off as they move between sunlight and shadow, creating discrete puffs of material that flow outward, each puff forming a shell expanding with the same velocity, but emitted at slightly different times. Seen from the side, these shells create a striated appearance. Or the pulsing could be intrinsic, the result of unstable sublimation, where ice venting creates fractures that temporarily vent more gas before sealing and opening elsewhere. Both mechanisms were known in cometary science. But there was another interpretation of the striations. If the jets were not thermally driven, but instead represented discrete thrust events from artificial engines, the pulsed structure would reflect the engine. Firing pattern, sustained thrust from a rocket engine does not look like random flickering. It looks controlled, periodic, structured. If you were observing exhaust from a spacecraft making trajectory corrections, you might see exactly this kind of pulsed emission. The pattern would depend on the control algorithm, how frequently the thrust is fired, how long each burn lasted. It was impossible to distinguish between these scenarios from images alone. You needed velocity measurements, composition analysis, higher resolution than ground-based optical telescopes could provide. The frustration in the scientific community was palpable. Every new observation provided more data but not more clarity. The tail was growing, that was clear. It was complex, that was clear. But what that complexity meant remained ambiguous. Was it complicated cometary activity driven by unusual but natural composition and geometry? Or was it something else? The observations were entirely consistent with either interpretation. That ambiguity was scientifically unsatisfying. Science seeks to distinguish between competing hypotheses by finding observations that different hypotheses predict differently. But 3IATLAS was not cooperating. It presented a morphology that both natural and technological explanations could accommodate. Still, the tail was beautiful. That aesthetic dimension mattered even if it did not help resolve scientific questions. The images of 3IATLAS with its multiple streaming tails, captured against starfields and distant galaxies, were genuinely striking. They looked alien in the sense of unfamiliar, strange, other. Whether that strangeness reflected extraterrestrial intelligence or just the universe being weirder than our models predicted was unclear. But the strangeness was real. The object did not look like the comets in textbook illustrations. It looked unusual, and that unusualness kept people engaged, kept them watching, kept them wondering. The growing tail also meant that as 3IATLAS receded from the Sun and from Earth, it was becoming more visible rather than less. The increased activity compensated for the increasing distance. This extended the observational window. Objects that fade predictably according to inverse square laws become too faint to study relatively quickly. 3IATLAS was not fading as fast as predicted. That gave astronomers more time to collect data, more opportunities to schedule telescope time, more chances to answer questions. Whether this extended visibility was a fortunate accident of composition and geometry, or something more deliberate was, like everything else about 3IATLAS, open to interpretation. But while astrophotographers captured the growing tail from their observatories and backyards, while Loeb analysed the implications and critics disputed his analyses, while the tail structure was discussed on internet forums and in academic colloquia, another story was quietly developing, one that would resonate differently from the telescopic observations and mathematical arguments. Because not everyone observing 3IATLAS was using million-dollar instruments at professional facilities or even $1,000 telescopes in private observatories. Some observers were using equipment that cost less than a nice dinner for two, and they were succeeding. They were capturing images of an interstellar object from light-polluted city centres using consumer-grade smart telescopes that could fit in a backpack. The democratization of astronomy was about to have its moment, and it would show that in the modern era, you did not need credentials or expensive equipment or special access to participate in cosmic discovery. You just needed curiosity and a clear sky. Amateur astronomers were about to prove their worth in ways that would surprise even professionals who had been doing this for decades. Amateur revolution. When a $50 telescope changed everything. Stuart Atkinson woke at 4:30 in the morning. Freezing November air in Kendal, Cumbria, in the north of England. Frost on the ground, sky clear. He grabbed his C-Star S50 smart telescope, not much larger than a shoebox, and headed to the river. The sky was not dark. Not really. Kendal is a town of 30,000 people, and the light pollution is significant. The moon was up, bright, adding its glow to the streetlights and the pre-dawn twilight. 3IATLAS was low in the sky, scraping the treetops, at an angle where atmospheric distortion would be severe. These were awful conditions, exactly the opposite of what professional astronomers require for quality observations. Dark sky sites are selected for their lack of light pollution. Observations are scheduled when the moon is down. Objects are best observed when high in the sky where the atmosphere is thinnest. None of these criteria were met. Atkinson knew the odds were against him. The C-Star database did not include 3IATLAS yet, so he could not just tell the telescope to point at it automatically. He would need to star hop, identify the field manually, hope he got close enough that the object would appear in the frame. His first attempts were awful. Images covered in streaks of glare from the moon and nearby lights. He was ready to give up. This was not going to work. But he adjusted, shielded the telescope better, let his eyes adapt, refined the pointing, tried again. And there it was, faint, barely distinguishable from background noise, but unmistakable once you knew what you were looking for, a fuzzy patch that did not match the stars. 3IATLAS, captured from the centre of a light-polluted town with a smart telescope that cost less than some people spend on coffee in a month. The image was not pristine. It was not going to win astrophotography competitions, but it showed the object, it showed the coma. With processing, you could even see hint of a tail. An interstellar visitor, 7 billion years old, travelling at 130,000 miles per hour, visible in a consumer-grade telescope operated by an amateur from his local riverbank. This was revolutionary. Not because of the specific observation, though that was valuable. Revolutionary because of what it represented. For most of human history, astronomy was limited to what the naked eye could see. Stars, planets, the moon, comets if they came bright enough. Then telescopes were invented and a new realm opened. But telescopes required money, expertise, access to dark sites. Even into the late 20th century, astrophotography meant dealing with film, long exposures, manual tracking mounts that required constant adjustment. It was technically demanding and expensive. Only serious hobbyists could do it. The digital revolution changed things gradually. CCD cameras replaced film. Computer-controlled mounts improved tracking. Image processing software made enhancement easier, but there was still a significant barrier to entry. The equipment cost thousands. The learning curve was steep. You needed to understand optics, mount polar alignment, image acquisition parameters, processing workflows. Astrophotography remained a specialized hobby. Smart telescopes like the Sea-Star changed the equation entirely. Point it at the sky. Tell it what you want to see. It figures out where that is, points itself automatically, takes multiple exposures, stacks them internally, processes the result, displays it on your phone. No polar alignment, no guide scopes, no manual camera settings, no post-processing software. The entire complexity is hidden behind a user interface designed for simplicity. You do not need to know how it works. You just need to aim generally in the right direction and let the automation handle the details. And the cost. The Sea-Star S50 retailed for less than 500 currency units depending on market and timing. Less than a good eyepiece for a traditional telescope. Less than a decent camera body without any lens. For that price, you got a complete system. Telescope, mount, camera, computer, wireless connectivity, all integrated. Compare that to a traditional astrophotography setup, which could easily exceed 10,000 currency units for equivalent capability. The price difference was not incremental. It was order of magnitude. It meant that people who would never have considered astrophotography because of cost could now participate. The Sea-Star was not alone. Multiple companies had released smart telescopes in recent years. Stellina, Vespera, Eviscope, others. Each with slightly different features and price points, but all following the same philosophy. Make it easy. Make it accessible. Hide the complexity. Let the technology do the hard part so the user can focus on the experience of discovery. The democratization of astronomy was not aspirational. It was happening. It was real. Atkinson's image of 3IATLAS represented proof of concept. If you could image an interstellar comet from a light-polluted town in England with a budget-smart telescope, then anyone could. Geography no longer mattered as much. Light pollution was still an issue, but not insurmountable. Equipment cost was no longer prohibitive. The knowledge barrier had been lowered to the point where someone could go from zero to capturing an interstellar object in a single observing session. This was unprecedented. The implications extended beyond individual observers. When thousands of people have the capability to image objects like 3IATLAS, the amount of data available explodes. Professional observatories could point their instruments at 3IATLAS for a few hours per month. Amateurs worldwide could observe it every clear night. Hundreds of locations. Continuous coverage as the Earth rotates, bringing new observers into darkness. Time resolution that no professional survey could match. And importantly, diversity of perspective. Different latitudes see objects at different angles. Northern Hemisphere observers see 3IATLAS from one vantage. Southern observers see it differently. Every observation adds a slightly different view. Amateur contributions to comet science had always been significant, but they were typically dominated by serious hobbyists with substantial equipment investment. The smart telescope revolution brought in a new population. Casual observers, people curious enough to buy a gadget and point it at something interesting, but not committed enough to learn traditional astrophotography. That population was much larger than the population of serious amateur astronomers, and their observations, while individually perhaps less sophisticated than what serious amateurs produced, were collectively valuable. The discovery potential was real. Professional surveys were designed to find known types of objects in expected places, asteroids in the asteroid belt, comets brightening as they approached the sun, supernovae in distant galaxies, but unexpected objects in unexpected places could be missed if they did not fit search parameters. Amateurs looking at fields for aesthetic reasons or out of curiosity might notice something the surveys missed. One Oumuamua was discovered by a professional survey, but only after it had already passed its closest approach to Earth. If amateurs with wide-field smart telescopes had been looking at that part of the sky, they might have caught it earlier, provided more warning, enabled more observations while it was still bright enough for detailed study. 3IATLAS benefited from this amateur network. Every image contributed to understanding its brightness evolution, tail structure, position in the sky. When professionals published papers about 3IATLAS, many of the observations they cited came from amateurs. The acknowledgement sections listed names of people with no institutional affiliation, independent researchers, citizen scientists, hobbyists who happened to capture important data because they were in the right place at the right time with their equipment. But there was also something intangible about amateur participation, a sense of ownership. When you personally capture an image of an interstellar object, you have connected with it in a way that reading about it or seeing professional images cannot match. That photons from 3IATLAS travelled across the solar system, entered your telescope, struck your sensor, were converted to electrons and processed into an image you can see that creates a relationship. You were there. You witnessed it. Not through the mediation of professional scientists or news reports, but directly through your own observation. That directness fostered engagement and interest that passive consumption could not. Schools were taking notice. Smart telescopes provided opportunities for educational programs that traditional telescopes could not match. A school could purchase a sea star, have students take turns observing different objects, build curriculum around the images captured. No need for a dome or a permanent observatory. The telescope could be stored in a closet and carried outside when needed. No special training required for faculty. The automation meant that even teachers without astronomy background could supervise observations. This was educational technology that actually lowered barriers rather than raising them. 3IATLAS became a favourite target for educational observations because it was timely and interesting. Showing students an interstellar visitor was inherently exciting in a way that showing them Andromeda Galaxy, while scientifically important, might not be. This was an object with a story, an object being debated by scientists, an object that might tell us something about the universe beyond our solar system. Students could participate in that excitement by imaging it themselves. The images students captured were scientifically useful. Amateur observations from any source, including schools, contributed to the collective data set. A middle school in rural area with clear skies might capture better data than a professional observatory during cloudy nights. The distributed nature of the amateur network meant that atmospheric variations, weather patterns, local seeing conditions, all averaged out across hundreds of observers. Someone somewhere was always observing 3IATLAS on any given night. That continuity was valuable. Critics of amateur contributions sometimes argued about data quality. Amateurs do not calibrate as carefully. They might not flat field images to correct for sensor irregularities. They might not apply photometric standards. Their astrometry might be less precise. All of this was true, but it also missed the point. Amateur data was not meant to replace professional data. It was meant to complement it. Amateurs provided coverage, time series, event detection. If something changed about 3IATLAS, suddenly amateurs would notice because someone was always watching. Professionals could then point their instruments for detailed follow-up. The two communities were synergistic, not competitive. There was also the human angle. Science benefits from public support. Funding for research comes from taxpayers through government agencies, or from philanthropic sources, or from universities with public missions. That funding is easier to secure when people care about science, when they see it as relevant to their lives, when they feel connected to the process of discovery. Amateur astronomy creates that connection. It turns space science from something abstract that happens in distant observatories into something tangible that happens in your backyard. That tangibility translates to support. Atkinson shared his 3IATLAS image on social media. It spread rapidly, not because it was technically superior to professional images, but because of the story behind it. Guy in England with cheap telescope captures interstellar comet from polluted city. That narrative resonated. It said that you do not need to be special to participate in this. You do not need credentials or expensive equipment or perfect conditions. You need curiosity and persistence. The image was proof that ordinary people could do extraordinary things if given access to the right tools. Other amateurs posted their own 3IATLAS captures. Different equipment, different locations, different processing approaches. Each image slightly different, reflecting the unique circumstances of its creation. Together they formed a mosaic, a collective portrait of 3IATLAS assembled from hundreds of individual contributions. No single professional observatory could have produced that mosaic. It required distributed observers, different perspectives, sustained effort over time. It required the amateur community. The smart telescope revolution was still in its early stages. The technology was improving rapidly, sensors getting more sensitive, processing algorithms getting more sophisticated, prices dropping as production scaled. In few years, the capabilities of budget smart telescopes would rival what serious amateur telescopes provided a decade earlier. And in few more years after that, perhaps they would rival what professional small telescopes could do. The trend was clear. The gap between professional and amateur capability was narrowing. Not eliminating, professional facilities would always have advantages of size, specialized instruments, dark sites, but narrowing enough that the distinction was becoming less meaningful for many types of observation. 3IATLAS would be remembered not just for its anomalies and the debates it sparked, but also for being the object that demonstrated the power of democratized astronomy. That showed what was possible when tools became accessible to everyone. Future interstellar visitors would be observed by an even larger network of citizen scientists. Each new generation of equipment bringing more people into the community, each observer contributing their small piece to the collective understanding. Science was becoming less hierarchical, more distributed, more participatory, and that was fundamentally good. Not because it threatened professional astronomy, but because it enriched it. Because it expanded the base of people who cared about cosmic questions. Because it turned viewers into participants. But even as amateurs celebrated their successful captures of 3IATLAS, even as the smart telescope revolution empowered thousands of new observers, the object itself continued its relentless journey outward, every day farther from the sun, every day dimmer, every day closer to the moment when it would fade beyond even the most sensitive amateur equipment and become once again the exclusive domain of professional observatories. That moment was coming, not immediately, but inevitably. The window for easy observation was finite. In weeks, 3IATLAS would reach its closest point to Earth. After that, it would recede and fade rapidly. The amateur revolution had happened at the perfect moment. A little earlier, and the object would have been too faint. A little later, and it would already be gone. Timing mattered in astronomy as much as technology, and for 3IATLAS the timing had aligned to let as many people as possible witness this rare visitor. The next step in that timing was approaching fast, the closest approach to Earth, the moment when 3IATLAS would be as close as it would ever get, when observations would be at their best, when questions might finally find answers. December 19th was marked on calendars worldwide. Scientists planning their observations, amateurs clearing their schedules, everyone wondering what that closest approach might reveal, whether it would clarify or deepen the mystery, whether 3IATLAS would give up its secrets or carry them back into interstellar space. The countdown had begun. December 19th. The closest approach. And what it means. 170 million miles. That is the distance 3IATLAS will reach at closest approach to Earth. Sounds close when you say it quickly. 170 million miles. But distance in space has a way of defying intuition. That is 1.8 astronomical units, 1.8 times the distance from Earth to the Sun. If you could somehow travel at highway speeds, 60 miles per hour, it would take you 324 years to cover that distance. If you were in a commercial jet going 500 miles per hour, it would still take 39 years. Even light, the fastest thing in the universe, takes 15 minutes to cross that gap. By astronomical standards, this is close. By human standards, it remains incomprehensibly far. But distance is relative. 3IATLAS reached perihelion at roughly 1.4 astronomical units from the Sun, just inside Mars' orbit. It passed within 0.2 astronomical units of Mars, close enough that spacecraft orbiting the red planet could observe it with useful resolution. It will pass 1.8 astronomical units from Earth, 9 times more distant than its Mars encounter. After Earth, it continues outward toward Jupiter, reaching within roughly 0.3 astronomical units of that giant planet. These close approaches are not coincidental. Loeb calculated the probability of a random interstellar trajectory bringing an object this close to multiple planets, while remaining unobservable from Earth during perihelion. The probability was low, very low. Low enough to add to his list of anomalies, suggesting that maybe the trajectory was not random, that maybe 3IATLAS came this way deliberately. The skeptics had responses. Space is big, but the planetary orbital plane is relatively compact. Objects on retrograde orbits, travelling opposite to the planet's direction around the Sun, naturally spend time near the ecliptic plane where the planets orbit. If an interstellar object enters the solar system at an angle, conservation of angular momentum means its trajectory will precess, wobbling above and below the ecliptic. Depending on entry angle and velocity, it could easily pass near multiple planets purely by geometric chance. The probabilities Loeb calculated assumed random entry from all directions, but interstellar objects might preferentially come from certain directions in the galaxy, from the direction of stars that passed near the Sun in the past, from regions where stellar encounters are more common. If you account for those directionality biases, the probabilities shift. Maybe not dramatically, but enough to make the trajectory less improbable than it initially appeared. The December closest approach mattered because it represented the last good opportunity for detailed observation from Earth. Before perihelion, 3IATLAS was brightening but still distant. During perihelion, it was behind the Sun. After perihelion, it was emerging back into view but receding. The closest approach caught it at a moment when it was still relatively bright, high enough in the sky for good observation geometry, far enough from the Sun to avoid glare. Observing windows like this are finite. You observe when you can. The magnitude prediction suggested 3IATLAS would be around magnitude 12 during closest approach. Magnitude 12 is not visible to naked eye, not even from the darkest sites on Earth. You need a telescope. But magnitude 12 is well within reach of amateur instruments. Any decent backyard telescope with a camera can detect it. Smart telescopes can image it. Binoculars from dark sites might show it as a very faint smudge if you know exactly where to look and have excellent vision. The object was accessible to a broad audience, not just professionals. The constellation Leo would host 3IATLAS during its closest approach. The comet would be rising around 2300 hours, becoming visible in the late evening rather than requiring pre-dawn observation. It would be located not far from Regulus, the brightest star in Leo, providing an easy reference for locating it. Charts showing the precise position on December 19th circulated through amateur astronomy forums. Star-hopping guides explained how to find it. Apps updated their databases to include 3IATLAS. The infrastructure for observation was in place. What scientists hoped to learn from closest approach observations depended on which questions they were asking. Those studying 3IATLAS as a natural comet wanted high-resolution spectroscopy. They needed to measure the velocities of material in the jets. If the outflow speed was consistent with thermal sublimation, a few hundred meters per second, that would support the natural interpretation. If velocities were higher, thousands of meters per second, that would imply different physics. Chemical rocket exhaust, ion thruster exhaust, something energetic happening beyond just ice warming in sunlight. Spectroscopy could also determine composition with greater precision. The nickel-to-iron ratio that had been so surprising needed confirmation with better data. Was it genuinely as extreme as initial measurements suggested? Or had there been errors, calibration issues, contamination from terrestrial sources? December observations with large telescopes and long integration times could answer this. They could also look for other elements, signature of industrial processes, isotope ratios that might indicate synthesis rather than natural formation. The composition was a key piece of the puzzle. Photometry over time would track brightness changes. If 3IATLAS was rotating, its brightness should vary periodically as different surface areas and reflectivities turn toward Earth. The 16-hour period measured earlier in the year could be checked. Had the rotation changed? Sped up due to asymmetric outgassing torque? Slowed due to braking from jets? Stayed constant? Rotation period contains information about the nucleus shape and mass distribution. Changes in rotation period indicate torques, forces acting on the object. This was basic physics, but applying it required careful observation. High-resolution imaging if the HiRISE data was ever released, if other spacecraft opportunities arose, if ground-based adaptive optics could resolve the nucleus, would show surface features. Was the nucleus monolithic, irregular, contact binary, rubble pile? Did it show craters? Did it show structure suggesting fracturing or layering? Natural cometary nuclei have characteristic appearance, shaped by sublimation and impacts and thermal cycling. Technological objects would look different. Smooth surfaces, geometric features, regularity. Humans recognize technology when we see it, because technology bears the marks of design. A spacecraft looks like a spacecraft. The question was whether imaging could reach resolution sufficient to see such features if they existed. Astrometry would refine the trajectory. The more precisely you measure an object's position over time, the better you can calculate its orbit, determine where it came from, predict where it is going. 3IATLAS had an eccentricity over 6, hyperbolic, definitely unbound to the Sun. But the exact value mattered. The trajectory could be backtracked to determine which direction in the galaxy it came from. Did that direction align with any known stars that 3IATLAS might have visited? Could you trace its path through the interstellar medium, determine how long it had been travelling? Where was it billions of years ago when it formed? These were questions astronomy could answer given sufficient data. December 19th also mattered psychologically. For the public following the story, this was the climax, the moment when 3IATLAS was closest. After this, it would leave. The closest approach represented a peak, and peaks are emotionally significant even when the physical changes are gradual. The difference between 1.8 astronomical units and 1.9 astronomical units is not dramatic in terms of what you can observe. But crossing that threshold, passing the moment of closest approach, knowing that from then on it's only getting farther, that changes how people engage with the event. Media coverage would likely spike around December 19th. News outlets that had been periodically checking in on 3IATLAS would do special features. Where is it now? What have we learned? What remains mysterious? These human interest angles drove coverage as much as scientific updates. The narrative arc required a climax, and closest approach provided that structurally, even if scientifically, it was just another point on the trajectory. Loeb had been clear about what December observations needed to show to support the technological hypothesis. High jet velocities, evidence of collimation beyond what radiation pressure could achieve, spectroscopic signatures inconsistent with thermal processes, stability of the nucleus despite mass loss that should have fragmented it, rotation behaviour that did not match natural outgassing torques. The more of these boxes that got checked, the stronger the case became. The more they could be explained naturally, the weaker. But there was also the possibility that December 19th would be anticlimactic scientifically, that observations would show exactly what was expected from a comet at that distance, that the anomalies that seemed so significant in earlier data would fade or find explanations as better observations refined the measurements. This was always possible. Anomalies often dissolve under scrutiny. What looks like a signal in preliminary data becomes noise when you account for uncertainties properly. 3IATLAS might be a comet, that just happened to be unusual in several ways simultaneously. Unusual but not impossible, not technological, just weird. The December observations would not definitively settle anything. That much was already clear. Even best-case scenarios, perfect weather, flawless execution, maximum integration time on the largest telescopes would still leave ambiguities. You cannot prove something is technological from astronomical observation alone unless it does something so obviously artificial that no natural process could explain it. Accelerating at implausible rates, emitting radio signals with structured information, showing geometric shapes visible in imaging. Short of such smoking guns, the natural versus technological debate would continue, and 3IATLAS had not provided smoking guns. It had provided anomalies, 12 of them by Loeb's count, each individually explainable with some effort, collectively suggesting something was off. But off did not mean alien. Off meant our models were incomplete. Maybe 3IATLAS was teaching us that interstellar comets are different from solar system comets, in ways we had not anticipated. Maybe the chemistry of interstellar space, the radiation environment, the timescales involved in travelling between stars, all created objects with properties that our models built from studying local comets did not predict. That would be fascinating science. It would expand our understanding. It would not require invoking intelligence. The tension between wanting clear answers and accepting ambiguity was palpable in the community. Scientists trained to live with uncertainty, to wait for sufficient data before drawing conclusions. But scientists are also human. They have intuitions. They form opinions. Some were convinced 3IATLAS was natural, that Loeb was overinterpreting noise, that the technological hypothesis was premature. Others were less certain, not convinced it was artificial, but willing to consider the possibility seriously. A small minority agreed with Loeb that the evidence warranted technological interpretation. Those positions were not going to shift dramatically based on December observations alone, unless something truly unexpected appeared. What December observations would do is provide data for future analysis. Papers would be written, peer review would scrutinize the methods and conclusions. The scientific process would grind forward at its characteristic pace. 5 years from now, looking back, researchers would have much clearer picture of 3IATLAS. They would have had time to refine models, consider alternatives, replicate measurements. The questions that seemed urgent in December would be answered or discarded as unanswerable with available data. New questions would have emerged. That was how science worked. Not in dramatic revelations, but in gradual accumulation of understanding punctuated by occasional insights. But 5 years was the timeline of Loeb's bet with Schirmer. By the end of 2030, undisputable evidence of extraterrestrial technology or nothing. 3IATLAS alone might not constitute undisputable evidence, even if every anomaly remained unexplained. But it was a data point. It was the beginning. If 3IATLAS was followed by another interstellar object with similar anomalies, and then another, the case would strengthen. Or if the Galileo Project observatories detected objects near Earth, showing characteristics that defied natural explanation, that would count. The bet was not solely about 3IATLAS. It was about the broader search for technological signatures. 3IATLAS had simply been the catalyst that made the search feel urgent and real. December 19th was marked. Astronomers prepared. Amateurs cleared schedules. Professional observatories allocated telescope time. Spectroscopic instruments were reserved. Imaging campaigns were coordinated across multiple sites to ensure continuous coverage despite weather and seeing variations. The closest approach would happen regardless of human observation. 3IATLAS would reach its minimum distance from Earth whether anyone looked or not. But the scientific community intended to look, intently, with the best instruments available, trying to wring every possible piece of information from this fleeting encounter with an object from between the stars. And when December 19th passed, when the observations were collected and the data began its journey through analysis pipelines and publication processes, attention would shift. Not away from 3IATLAS entirely. The object would remain interesting as it receded, dimming slowly, still visible to large telescopes for months or years. But the sense of immediacy would fade, the urgency would diminish, the public interest would move on to other topics, and scientists would return to the slower work of interpretation, figuring out what 3IATLAS was, what it meant, what it taught us about the universe. Those answers would take time, but time was what science had. Time and patience and the determination to understand even when understanding came slowly and ambiguously. December 19th was just a milestone. The journey of understanding 3IATLAS would continue long after that date passed into history, long after the object itself had faded beyond visibility, long after the debates had quieted. The data would remain, the questions would remain, and somewhere out there, 3IATLAS would continue its journey, carrying whatever secrets it held back into the darkness between the stars. But December would bring more than just the closest approach. It would also bring something else, something that had been building beneath the surface of the 3IATLAS story from the beginning. The scientific debate had been intense, but largely confined to academic channels, papers, conferences, blogs read by scientifically literate audiences. The public had been interested, but not deeply involved in the technical arguments. That was about to change, because the argument was about to spill out into the open in a way that even casual observers could not miss. Two scientists, opposing views, public confrontation. The Wright versus Loeb war was about to begin in earnest, and it would show just how personal scientific disagreements could become when the stakes felt existential and the spotlight was bright enough to make everyone uncomfortable with ambiguity. The Wright versus Loeb war science's most public battle. The gloves came off in early autumn, not gradually, not with the usual academic politeness that characterizes most scientific disagreements. Jason Wright, astronomer at Pennsylvania State University, published a blog post that systematically dismantled every anomaly Loeb had catalogued about 3IATLAS. Not some of them, not the weakest arguments, every single one. The title alone set the tone. Loeb's 3IATLAS anomalies explained, not discussed, not examined, explained, as if the matter were settled, the case closed, the mystery solved by someone finally willing to do the actual work. Wright is not a random critic. He works on techno-signatures, on SETI, on the search for evidence of technological civilizations beyond Earth. He and Loeb had collaborated before, had been on the same side of arguments about how seriously we should take the possibility of artificial objects in space. Wright had even been one of Loeb's defenders early in the Oumuamua controversy, back when suggesting that first interstellar object might be technological was fresh and shocking rather than Loeb's standard operating procedure. So when Wright turned his attention to 3IATLAS and concluded that Loeb was wrong about essentially everything, it carried weight that criticism from a more conservative astronomer might not have. The blog post was detailed, thorough. It went through each anomaly one by one, explaining in accessible language why the seemingly bizarre behavior of 3IATLAS was actually perfectly consistent with natural cometary processes if you understood the physics correctly. The retrograde trajectory aligned with the ecliptic, not as unlikely as Loeb's statistics suggested, because the calculation ignored important factors about how the ecliptic relates to galactic structure. The anti-tail pointing toward the Sun, a well-documented phenomenon in comets with large dust particles that don't get swept away by radiation pressure as efficiently as smaller grains, the extreme nickel-to-iron ratio, based on preliminary measurements that other researchers had already questioned, and besides, comets show all sorts of compositional variations, on and on through the list. The fine-tuned arrival time that brought it near multiple planets, while being unobservable from Earth at perihelion, selection bias, because we only discover interstellar objects that pass relatively close to us, and perihelion geometry is constrained by orbital mechanics, the non-gravitational acceleration, completely normal for an active comet, and the amount detected was well within the range of what outgassing can produce. The jets maintaining orientation despite rotation. Wright pointed to detailed models of how asymmetric outgassing from topographic features can create exactly this kind of structure, complete with citations to papers about other comets that showed similar behaviour. It was a masterclass in scientific rebuttal. Every claim Loeb made was met with a counter-explanation grounded in established cometary science, complete with references to peer-reviewed literature and links to relevant observations of other objects. Wright was not dismissive in the sense of simply saying Loeb was wrong and moving on. He was dismissive in the much more devastating sense of showing his work, of demonstrating that for each anomaly, Loeb trumpeted as evidence of something extraordinary. There existed a perfectly mundane explanation that Loeb had apparently either overlooked or chosen to ignore. Loeb's response was swift and uncompromising. He compared Wright and other critics to artificial intelligence systems trained on limited datasets. If you train an AI only on data about comets, he wrote, it will insist that everything in the sky is a comet regardless of what anomalies the object displays. The comparison was deliberately provocative. He was not just defending his analysis of 3IATLAS, he was attacking the entire framework of thought that led astronomers to default to natural explanations. He called it the arrogance of expertise, the Pavlovian resistance to new ideas as a means of protecting turf of past knowledge. This was no longer a scientific disagreement. This was a clash of world views about how science should operate. Wright represented the position that extraordinary claims require extraordinary evidence, that when you have a phenomenon that looks weird, your first obligation is to exhaust all conventional explanations before invoking something unprecedented. Loeb represented the position that curiosity should outweigh conservatism, that the history of science is full of examples where the establishment dismissed revolutionary ideas because they challenged existing paradigms, and that we should take seriously the possibility that some objects might be technological, even if the majority turn out to be natural. The public watched this play out in real time through blog posts and Medium articles and social media threads. Wright would publish a detailed takedown of Loeb's latest claims. Loeb would respond not by addressing the specific technical points, but by reframing the argument as being about scientific methodology itself, about whether we should be bold explorers or timid gatekeepers. Wright would counter that being bold is not the same as being credulous, that rigour matters, that you cannot just wave away inconvenient physics because it interferes with a more exciting narrative. And the comment sections exploded. Some readers sided firmly with Wright, relieved that someone with credentials and knowledge was finally pushing back against what they saw as Loeb's increasingly reckless speculation. Others rallied to Loeb's defence, arguing that Wright was exactly the kind of closed-minded establishment figure that Loeb described, someone so invested in conventional wisdom that he could not recognise genuine anomalies even when they were staring him in the face. The arguments were often bitter, frequently personal, occasionally insightful. What made this particularly fascinating was that both men were arguing in public, rather than through the traditional channels of academic discourse. No peer-reviewed papers going through months of revision and response. No careful diplomatic language designed to criticize ideas without offending colleagues. Just raw, immediate, unfiltered disagreement published on blogs that anyone could read, complete with comment sections where non-experts could weigh in alongside professionals. It was science communication in the social media age, transparent and messy and utterly captivating for anyone interested in how scientific arguments actually unfold. Wright kept returning to the specifics. Here is what the data actually shows. Here is what the physics actually predicts. Here is why Loeb's interpretation requires you to ignore these measurements or dismiss these well-established principles. He pointed out errors in Loeb's calculations, instances where Loeb had apparently misunderstood the geometry of solar-wind interactions or the behavior of radiation pressure on dust grains. He documented cases where Loeb cited papers that actually contradicted the conclusions Loeb drew from them. It was thorough, detailed, and increasingly frustrated in tone as Loeb continued to publish new articles making new claims without, in Wright's view, adequately addressing the problems with the old ones. Loeb kept returning to the big picture. Here is why the conventional explanations are unsatisfying. Here is why we should not let expertise become a prison. Here is why the accumulation of anomalies, even if each one individually might have a natural explanation, collectively suggests something unusual might be happening. He emphasized that he was not claiming 3IATLAS was definitely artificial, just that the possibility should be investigated seriously rather than dismissed reflexively. And he pointed to his track record in other fields, the 1,000 papers he had published in cosmology and black hole physics, where this same approach of bold conjecture, followed by rigorous testing, had been not just accepted but celebrated. The bet with Michael Shermer became a focal point in this debate. Loeb had put his money and his reputation on the line, wagering that within 5 years there would be undisputable scientific evidence for a technological artifact from an extraterrestrial civilization. To his supporters, this demonstrated genuine conviction and willingness to be held accountable. To his critics, it demonstrated that this was more about personal legacy and publicity than about careful science. Wright suggested that the bet was essentially unlosable for Loeb because the criteria for what counts as undisputable evidence were vague enough that almost any unexpected discovery could be spun as vindication. The scientific community was deeply divided. Some researchers, particularly younger ones without established reputations to protect, found Loeb's willingness to challenge conventional wisdom refreshing and important. They argued that astronomy had become too conservative, too quick to explain away anything unusual rather than seriously investigating it. Others, particularly those who had spent careers studying comets and asteroids, found Loeb's approach deeply frustrating. They saw someone with no background in planetary science making confident pronouncements about objects he did not really understand, ignoring decades of careful work that had elucidated how these bodies actually behave. And beneath the technical arguments, there was a deeper question about scientific credibility and public trust. Wright worried that Loeb's high-profile speculation about alien artifacts, when those speculations were not supported by the data in the view of most experts, undermined public understanding of how science works and what level of evidence is actually required before making extraordinary claims. Loeb worried that Wright's reflexive skepticism and appeals to conventional wisdom were exactly the kind of gatekeeping that prevents science from making revolutionary discoveries, that creates an environment where anything genuinely anomalous gets explained away rather than investigated properly. The debate became a referendum on Loeb himself. His supporters saw a brilliant iconoclast willing to ask uncomfortable questions and challenge entrenched interests. His critics saw someone who had started with legitimate scientific questions about Oumuamua, but had gradually transformed into something closer to a showman, someone more interested in generating headlines than in doing the hard work of rigorous analysis. Both sides could point to evidence. Loeb's constant stream of blog posts and media interviews, his genuine scientific credentials and history of important contributions to astrophysics, his willingness to make testable predictions and call for more data, his tendency to announce new anomalies before peer review, to make confident claims based on preliminary observations, to frame disagreements as battles between curiosity and closed-mindedness, rather than as legitimate scientific debates about interpretation of ambiguous data. What became clear as the Wright versus Loeb war intensified was that this was not going to be resolved by more data alone. Even when the HiRISE images were finally released, even when spectroscopic observations of the jets became available, even when all the measurements were in, Wright and Loeb would almost certainly interpret those results differently. Wright would find ways to fit them into natural comet models, invoking more complex but still conventional physics if needed. Loeb would emphasize any aspects that remained difficult to explain, any residual anomalies that suggested something unusual was happening. Because at its core, this was not really an argument about 3IATLAS. It was an argument about how we do science when we encounter something we do not fully understand. Do we default to natural explanations until absolutely forced to consider alternatives? Or do we entertain alternatives earlier in the process, using them as tools to sharpen our thinking, even if they ultimately prove wrong? Do we prioritize avoiding false positives, making sure we never wrongly claim something is artificial when it is natural? Or do we prioritize avoiding false negatives, making sure we never dismiss something as natural when it might actually be artificial? There is no objective answer to those questions. They are matters of scientific philosophy, of personal inclination, of what kinds of errors you find more troubling. Wright leaned heavily toward caution, toward the view that claiming something is artificial when you lack definitive evidence causes more harm than missing an actual artifact would. Loeb leaned toward boldness, toward the view that we have only one chance to study these interstellar visitors as they pass through, and if we default too quickly to natural explanations, we might miss the discovery of the century. 3IATLAS became the battleground where these two philosophies collided with maximum visibility and minimum restraint. The object itself, whatever it actually was, had achieved something remarkable. It had forced the astronomical community to confront fundamental questions about methodology and evidence and the social dynamics of scientific disagreement. It had revealed the fault lines between different generations and different subfields and different temperaments within the scientific community. And it had done all of this in public, with millions of people watching scientists argue with a passion and intensity usually reserved for political debates. The war between Wright and Loeb was not going to end anytime soon. 3IATLAS would eventually fade from view, would complete its passage through the solar system and return to interstellar space. But the questions it raised about how we investigate potentially anomalous objects, about the balance between skepticism and curiosity, about the role of public speculation in scientific research, those questions would persist long after the comet itself had vanished into the cosmic dark. And somewhere out there, beyond the orbit of Neptune, beyond the Kuiper belt, beyond the heliopause, 3IATLAS continued its journey, indifferent to the arguments raging about its nature, carrying whatever secrets it held back into the vast silence between the stars.